किशोर मंच एक खुला मंच है, आए जब भी चाहे। किशोर मंच एक खुला मंच है, आए जब भी चाहे। हर किशोर को मिलेगा अवसर, खुलती जाए राहें। आए जब भी चाहे, आए जब भी चाहे, आए जब भी चाहे, आए जब भी चाहे। हो कला सामाजिक ज्ञान, भाषा गणित या हो विज्ञान, कठिन नहीं है विषय कोई भी, करो जरा सा ध्यान। हो कला सामाजिक ज्ञान, भाषा गणित या हो विज्ञान, कठिन नहीं है विषय कोई भी, करो जरा सा ध्यान।
ये है
किशोर मंच।
Hello students, this is Rahmat Ali from Indirapuram Public School. In the last session, we have studied about the force on a current carrying conductor placed in a magnetic field. We studied the force between the two parallel conductors carrying current. Now, in today's session, we will study about the torque experienced by a coil placed in a magnetic field. We will study about the moving coil galvanometer, how to convert a galvanometer into voltmeter and ammeter. We'll begin with the topic torque on a rectangular coil carrying current placed in a magnetic field. Let a rectangular coil KLMN carrying current I is placed in uniform magnetic field B, making an angle theta. If KL is equals to Mn is equals to length L of the rectangle and Mn is equals to Kn is equals to B, the breadth of the rectangle, then the force on arm KL is FKL equals to BIL. According to Fleming's left hand rule, this force will be radially downward as shown in the diagram. Force on the arm LM is FLM equals to BIB cos theta. Once again, according to Fleming's left hand rule, the magnetic force will be upward in the plane of the paper. Now, the force on arm MN is Fmn equals to BIL. Fleming's left hand rule gives us the direction which will be radially upward. And arm NK is Fnk equals to BIB cos theta. Once again, using the same rule, we obtained the direction is downward in the plane of paper. From the situation, it is very clear that forces FLM and Fnk are equal in magnitude but in opposite direction. So, they cancel each other, whereas the force KL and force Mn are equal in magnitude, opposite in direction. These two forces are forming a couple. One force is acting downward, second force is upward. The two forces form a couple which tries to rotate the coil. So, the torque tau equals to force into the perpendicular distance between the two forces, which is B cos theta. Substituting these values, we get tau equals to BIL B cos theta. As we know, length and breadth are multiplied in the formula. So, torque tau equals to B I A cos theta. Here A represents the area of the loop. If plane of the coil is making an angle alpha with the magnetic field, then alpha plus theta is equal to 90 degree. So, cos theta will be equals to cos 90 minus alpha, which comes to be sin alpha. So, cos theta is equals to sin alpha. Substituting this value, we get tau equals to B I A sin alpha. If number of turns in the coil be n, then the total torque tau will be equals to n B I A sin alpha. In the vector form, we can write it as tau equals to m cross b. Here m represents the magnetic moment of the loop, and the SI unit of this magnetic moment is ampere meter square. Moving coil galvanometer. It is a device which is used to detect the presence of current in the circuit. It works on the principle that when a rectangular coil carrying current is placed in uniform magnetic field, then it experiences some torque. Let's study its construction. It consists of a rectangular coil having n turns placed in uniform radial magnetic field B. The coil is wound on a soft iron core. If area of each turn in the coil is A, then torque tau will be equals to n B I A sin alpha. As the field is taken to be radial, so alpha equals to 90 degree. So, the maximum torque tau will be equals to n B I A. Due to this torque, coil will rotate in the magnetic field. In the construction of a moving coil galvanometer, we connect a spring having force constant K. The spring is attached to the coil as shown in the diagram. This spring opposes the rotation of the coil. If at any instant the coil is rotated by an angle theta, then the restoring torque tau will be equals to K into theta. At equilibrium situation, the torque n B I A is equals to K into theta. From here, we can calculate I equals to K into theta divided by n B A. Knowing the values of theta, we can calculate the current through the circuit, because K will be given for a particular galvanometer, number of turns, magnetic field and area of the coil all will be constant for the given galvanometer. Depending upon the different values of theta, we make a scale for a given galvanometer to read the corresponding values of the current. Sensitivity of a galvanometer. It is defined as the deflection in the galvanometer per unit current. If current I is passing through the galvanometer and the maximum deflection in the galvanometer for the corresponding current is theta, then the sensitivity Is is equals to theta divided by I. Substituting the value of the current, we get Is equals to B A N upon K. In order to increase the sensitivity of the current, we increase the value of magnetic field B and we decrease the value of force constant K. By doing so, the current sensitivity increases. We do not increase area of the coil in order to increase the sensitivity. The reason behind it is that it becomes difficult to maintain uniform magnetic field for larger area. We do not increase the number of turns also, as by doing so the resistance of the galvanometer increases, which opposes the flow of charges through it. Shunt. As we know that a galvanometer is a very sensitive instrument, so it can be damaged when strong current passes through it. For safe operation of galvanometer, we shunt it. Now, shunt is defined as a small resistance which is connected in parallel across the given galvanometer, so that the extra current will pass through it. The diagram is there, which is representing that a galvanometer G is shunted by a resistance S. If maximum current which can be measured with the help of a galvanometer is Ig and the current in the circuit is I, then shunt across the galvanometer S will allow the extra current I minus Ig through it. According to Ohm's law, the potential difference across the terminals of the galvanometer and the shunt will be same. If the resistance of the galvanometer is G, then I minus Ig into S will be equals to Ig into G. This is the relation which we obtained using Ohm's law. From here, the value of shunt S is equals to Ig into G divided by I minus Ig. Conversion of galvanometer into ammeter. We know a shunted galvanometer is called an ammeter when whole setup is enclosed in a box as shown in the diagram. As I minus Ig into S is equals to Ig into G, so I into S will be equals to Ig into G plus S. So, the maximum current which can be measured using an ammeter I will be equals to Ig into G plus S divided by S. Knowing the values of S and Ig, we can calculate the value of current I. Resistance of an ammeter. As resistance S and the resistance of the galvanometer are in parallel to each other, so using the relation of parallel combination of resistors, we get 1 upon A is equals to 1 upon S plus 1 upon G. That means A equals to G into S divided by G plus S. Always remember, an ideal ammeter has 0 resistance and it is always connected in series combination of the cell. Conversion of galvanometer into voltmeter. In order to convert galvanometer into voltmeter, we connect a high resistance in series with the galvanometer. If R be the resistance connected in series with the galvanometer, then the total resistance of the galvanometer setup RV is equals to R plus G. So, the maximum potential difference measured by the voltmeter V equals to Ig into R plus G. Voltage sensitivity. It measures the deflection in the voltmeter per unit potential difference applied across the ends of the voltmeter. If theta is the deflection in the voltmeter when a potential difference V is applied across its terminals, then voltage sensitivity Vs is equals to theta upon V. Substituting the value of V, we get Vs equals to theta divided by Ig into R plus G. As we know, theta upon Ig is current sensitivity. So, Vs is equals to Ig divided by R plus G. Let us study a numerical based on the situation. Let we have a galvanometer of resistance 50 ohm which gives us full scale deflection when 50 milliampere current passes through it. If we have to convert this galvanometer into an ammeter so that it can read a current of 1 ampere, then we connect it with a shunt resistance S. According to the Ohm's law, I minus Ig current will pass through the shunt resistance S. So, I minus Ig into S equals to Ig into G. Substituting the values of current I, Ig, S and the value of G, we obtain 1 minus 0.05 into S equals to 0.05 into 50. From here, the value of shunt resistance S is equals to 0.05 into 50 divided by 0.95. After calculation, we came to know that the shunt resistance S should be equals to 2.63 ohms. So, it means if we want to convert galvanometer of 50 ohms into an ammeter which can measure a current of 1 ampere, then we have to shunt it with the resistance of 2.63 ohms. Let us study another numerical in which we have to convert a galvanometer of 50 ohm resistance into a voltmeter of 5 volt. when this galvanometer gives us full scale deflection at 50 millivolt. In this situation, the maximum current through the galvanometer Ig is equals to Vg divided by the resistance of the galvanometer, as the maximum potential difference Vg is equals to 50 millivolt. So, Ig equals to 50 into 10 to the power minus 3 divided by 50, which is equals to 10 to the power minus 3 ampere. We know the maximum potential difference measured by the voltmeter V equals to Ig into R plus G. So, substituting the value of V and Ig and the value of the galvanometer G, we come to know that 5 equals to 10 to the power minus 3 into 50 plus R. So, that means 5000 equals to 50 plus R, that is R equals to 4950 ohms. It means if we want to convert a galvanometer of 50 ohm resistance, which gives us full scale deflection at 50 millivolt, into a voltmeter of 5 volt, then we have to connect a series resistor of 4950 ohms with the given galvanometer. So, today in this session we have studied the torque experienced by a coil. We studied the moving coil galvanometer, how to convert this galvanometer into an ammeter and voltmeter, and we discussed two numericals also. In the next chapter, we will study the magnetic properties of substances like diamagnetic substances, paramagnetic substances, ferromagnetism. We will study the hysteresis and the application of hysteresis loop. That's all for today. Hope you enjoyed the session. Thank you.
I am Anuradha Mathur. I teach physics at Modern School Vasant Vihar, New Delhi. Today we will be talking about magnetism. Moving charges and electric currents are associated with magnetic field, a fact that was discovered in early 19th century by Ampere, Oersted, Boyd-Sawatz amongst others. Magnets have a special property. They have a field associated with it. Electric currents give the same property. This connection we will make and try and learn some properties of magnets and solenoids, compare the two, and thereafter find a solution and find the magnetic field due to a bar magnet along its axial line and along the equatorial line. Some basic properties of magnets are that earth behaves like a magnet and it has its field directed from the south, geographic south towards the north. If you have a freely suspended magnet like this compass needle, the end that points towards the north pole is called the north and the south seeking pole is called the south. Like poles of a magnet repel each other and unlike poles attract. There is a field around a magnet or space around a magnet where its influence can be felt. You might have done these experiments earlier, where you just sprinkle some iron filings onto a magnet and observe its pattern. This pattern is because there is a region of influence. It creates a pattern showing that there is a field around it, a region of influence, so to say. This field is three-dimensional in nature and therefore, you could talk about the magnetic field at a distance away from the magnet as well, which means that there should be some rules, some laws that will govern the magnitude of this field. Because current is associated with magnetic field, we have talked about magnetic moment, which in turn is given by m, the magnetic moment is equal to the current flowing through a loop into the area vector. The area vector becomes important because if the direction of current in the loop changes, then the area vector, which is the line perpendicular to the plane of the loop, is going to point in this direction, and this gives us the field pointing upwards. If you change the direction of current in the same loop, then the field would point in the opposite direction. This result shows that this is a vector quantity and so is this a vector quantity. If you were to increase the number of loops, then this would include the number of loops over there. We can take this idea from here and use it to calculate the magnetic field due to a bar magnet along two lines, one along its axis and along the line which is perpendicular to this axis. What will be the magnetic field at this location or at this one? In order to do that, I have over here an experiment which shows you the magnetic field lines because of a magnet and the field lines that are produced by a solenoid. In order to find the magnetic field due to this bar magnet along its axis, any point around here or on the equatorial line, we have over here an apparatus by which you can see the field lines due to the bar magnet and the solenoid being almost the same. These are the closed loops starting here, going all the way through the magnet. In this case also, from this end of the solenoid right around here and going all along the solenoid this way. So, closed loops which represent the field lines of a magnet are seen in these two, which are identical. You must know that the electric field lines and the magnetic field lines are different. In the case of electric field, the field lines originated from the positive charge and end at the negative. In this case, they are continuous loops. So, the field appears to be within the setup, within the magnet, within this solenoid and different from an electric field. Now, let us see. In order to calculate, let us make a picture of this solenoid. Say I represent it by this cylinder. Say the area of cross section is given in terms of the radius of this solenoid. It is a uniform radius solenoid. Say A is its radius. Say the length of the solenoid is 2L, and along here I want to find the field at this point P. This is its center. So, L from the center here and likewise. So, let us say the distance of this point from this central point here is some value r, and we want the field. So, let us imagine a small element somewhere around here like this, which would be my dx, and say it is at a distance of x from the center of the solenoid. Now, if you take this into account, you will use your Boyd-Sauert's law to give you the value for delta B on account of this current element which I have just colored. This will be equal to mu 0, the permeability here, into the current that is flowing through it, into the area square upon your 2 into r minus x the whole square plus a square, and the whole thing raised to the power of 3 by 2. Now, from here, if you were to find for the whole solenoid, then you would have to integrate it. So, the total field would be this, which would be mu naught I, we have left out the dx. So, dx should also be included, mu naught I into your a square upon 2, and if there are n turns per unit length, then you will account for that factor as well. And from minus L to plus L, from the center minus L would be this and this would be plus L, and this value, and all the way the denominator remains the same, r minus x the whole square plus a square raised to 3 by 2. This expression can be made as an approximation, and what is the approximation? That this point that we are selecting is at a distance which is much larger than the length of the magnet, as also the element that we considered for our solenoid is going to be very close to the center. So, our x value is very much less than r, and so is our L value less than r. So, we now get this expression B is equal to mu naught n I being the total number of turns, and I the current, a square upon 2 r cube. We had already talked about the magnetic moment being equal to the number of turns, which is n into 2 L, current flowing through the loop, and the area vector. This can be, the formula can be now written for B in terms of magnetic moment as mu naught 2 m upon 4 pi r cube. If you are to relate this value for the magnetic intensity with that of an electric dipole, you can then say that the value along the equatorial line would be exactly half of this. Now, you may argue, how can you take such a suggestion which is just talking in terms of two dipoles being the same? Well, if a dipole behaves in a particular way, other dipole should also behave much the same way. That is the reason why we are taking electric dipole value that we had obtained here mathematically to give us the value for magnetic field value, and you can write then half of this value will have just this. So, this becomes our magnetic field along the axial line, and this becomes the magnetic field along the equatorial line. Something very easy and simple. Some of the books and some people still argue that you should be talking about pole strength, but pole strength is no longer an option to talk about, because we are now going to be talking only in terms of magnetic current loops, electric current loops, and their associated magnetic dipoles. Therefore, all magnets are going to be treated as though made up of a large number of current loops, as we have just done. We can approximate this formula, and how is that? Because we can say that the distance r that we have selected is much larger than the length of the magnet. Also, the element that we have chosen to give us the value for B is very close to the center. So, our x value is also small as compared to r. Doing that, we are then going to get the formula as the magnetic field B to be equal to mu naught n into I 2 L A square divided by 2 r cube. Now, if I want to reduce or accommodate and adjust magnetic moment idea and the concept of magnetic moment idea, then m, as we had discussed earlier, is equal to the total number of turns multiplied by the value for current flowing through it into the area vector, which is pi a square. Using this m value in this expression, B along this line at the axial point, as we have calculated that, will become mu naught 2 m upon 4 pi r cube. This expression also is going to be very useful, because now what we are going to say is that if this magnetic dipole has the magnetic field value given by B along the axial line by this expression, if I relate it to an electric dipole, I can then predict the value along the equatorial line, which will be half of the value. Now, you may say that how can you just pick upon electric dipole and say that all right, just because electric dipole had this value, magnetic dipole should also have it. But you must always remember that all dipoles are going to have much of their fields in the same way or the same pattern, and that is why you can conveniently predict the value of magnetic field along the equatorial line to be equal to exactly half of that it is on the axial line. So, your value then becomes B is equal to mu naught m upon 4 pi r cube. Many books, many people argue that you should be giving the value of magnetic pole strength. Well, we are never going to be talking about a pole strength for a magnet, because now we are associating all magnetic fields to current loops, and therefore, it is always convenient and easy to say that a bar magnet also has circulating current loops, and therefore, by association, as we have calculated right now, you can always find the value for magnetic field from the center of the magnet. I have a magnet here and I cut it into half. So, what will be the magnetic field because of each of them? From our expression that we have just derived, we can see that the magnetic moment, the value for L will become half, and so each of them will have almost half the strength. This you can check by using a magnetic needle or a magnetometer disc. You can check this value to be becoming almost half of it. Supposing I were to cut the magnet into half like this. So, now I have two long magnets. What will be the pole strength in this case? Very interesting, because now our solenoid that we had with a radius of A will have a radius of A by 2. So, the field would become almost a quarter of what it is right now. Very simple and very interesting. So, you can do more calculations like this using this expression, answer all the typical questions that are asked about bar magnet, typically why can't you have a monopole, etc. So, from today's lesson we will conclude, and you have learned that magnetic properties, basic magnetic properties of a bar magnet, and you have used a solenoid and concept of magnetic moment associated with a current loop, and found the value for magnetic field intensity at a location along the axis of a magnet, and so also along the equatorial line of a magnet.
Hello viewers, today we are going to discuss the techniques of differentiation, and our very first very important rule, that is the chain rule, is our focus. The chain rule is a rule of finding derivative of functions which are composition of two or more functions. Let us take a short visit back to the understanding and the idea of composition of functions before we get down to the chain rule. Composition of functions can be very well understood if we look at a pair of function machines. Here we have a function machine G whose input is a ball, a sphere, and the output results in a cube. This output, when dumped into the function f, results in an output of a faceted ball. Together, they can be expressed as a big function machine where a ball is dropped in and it results in an output of a faceted ball. In mathematical terms, what does that mean? If I take x to be the input of G, it results in u as an output of G, same as g of x. This goes in the function machine f and results in an output f of u. Together, as I look at this as the composition, it would mean same as saying that x is the input and what is the output? Represented as f of g of x. That is exactly what we mean by composition of two functions. The chain rule is a rule of finding the derivatives of composition of two or more functions. Here is the rule without proof for you to follow and understand. If f is a composition of two differentiable functions f and g, that is f of x is same as, note the difference, that is a capital F is same as f of g of x, then capital F is differentiable and its derivative is product of the derivative of g and the derivative of f at g of x. So, it is same as f dash of g x into g dash x. Sounds confusing. Let us take another look at the same definition restated. Suppose capital F is the composition of small f and g, and let us call u to be g of x. Try to relate it to the picture that you had seen just a minute earlier. Then f of x is f of u, right? So, the chain rule says that derivative of f with respect to x is same as derivative of small f with respect to u, because now small f is a function of u. The output of g goes into f into the derivative of u with respect to x. So, there is a chain of continuation, there is a chain that you can see going from f to u, then u to x. So, you differentiate small f with respect to u, multiply it with the derivative of u with respect to x. That is what the chain rule of differentiation says. This gets extended to 3 or more functions, and we have a rule which says that if capital F is a function which is composed of f, g and h in that order, and if v is g of u, where u is h of x. So, you kind of come through the layers and you say h of x is u, and then the outer layer v, which will be g of u, such that the function capital F becomes f of v. Then what will be the derivative of capital F with respect to x? As I said, use chain rule, extend chain rule. What does it give us? Derivative of f with respect to v into the derivative of v with respect to u, because v is a function of u, into derivative of u with respect to x. This chain can be continued depending on the number of functions that are involved in the composition. Now, there is nothing that can replace actual application of the chain rule to get the hang of this rule. So, let us get down to applying this to our very first function. The question says differentiate sine of root x with respect to x. Notice that this is definitely a composition of two functions, sine function and the square root function. So, to find the derivative, we definitely need the chain rule. So, our function, let us call it capital F, is sine of root x, and let us take the inner function, inner as in this case the second function root x to be u, then f of x is nothing but sine of u, and therefore, by chain rule df by dx is same as the derivative of f with respect to u into the derivative of u with respect to x. That is same as cos of u, because derivative of sin u with respect to u is cos of u, into derivative of u, which is derivative of root x, is same as 1 by 2 root x. Replace u with root x and your answer is ready. Let us take a question where we have a little more complex composition. Here the question is, if y is equal to x plus root of x square plus a squared raised to the power n, show that dy by dx is n times y by under root of x squared plus a square. If you see the function y here, do you observe that there is composition involved? And not only composition, there is a sum of two functions as well, that is x plus under root of x square plus a square. This sum is raised to the power n. So, there is definitely more layers involved in this function. Let us see what we will do as we start the derivative. Let us take the inner function, that is the function which is the base, to be u. So, let u be x plus root of x square plus a square. So, clearly y is equal to u to the power n, and therefore, by chain rule the derivative of y can be read as derivative of y with respect to u into derivative of u with respect to x. Now, derivative of y with respect to u is nothing but n u to the power n minus 1. It is the derivative of u that needs more work. So, again going back to our function u, which is of course x plus root x square plus a square, it all simplifies, that is the derivative of y with respect to u simplifies to be this expression. Let us focus on u. U is x plus root of x square plus a square. It is just not sum of two functions. The second part of this function is again composition. So, let us just take that to be z. So, if z is root of x square plus a square, then the base function, that is x square plus a square, can be taken as w, and therefore, z becomes root of w. Are we ready then to find what dz by dx is going to be? So, dz by dx, that is the derivative of z with respect to x, is nothing but derivative of z with respect to w into derivative of w with respect to x, and that is nothing but 1 by 2 root w into 2x. Put back the value of w and you have the derivative of z with respect to x. So, our u, which was nothing but x plus z, has the derivative ready as 1 plus x by root x square plus a square, which may be again rewritten. But that is not the end of the problem. We go back to finding what dy by dx was. So, I already have dy by du and now I have du by dx. Using the chain rule, I have dy by dx written as the product of these two expressions. Notice that the two expressions which are being multiplied have something common. So, if you use the rule that if the base is same, powers get added, the expression does simplify to be nothing but n y by root x square plus a square, but because y was x plus root of x square plus a square whole to the power n. So, a more complex, more of a u, v, w and a z coming in sounds confusing and time taking as well. Will this be a practical approach for all the other problems that you come across? Well, may not. So, we need to reinvent our strategy and then use the chain rule. Let us take a problem and see if I can explain to you how to cut short this assumption of u, v, w. So, we have a question which says find derivative of cos of sine of root of a x plus b. Do you see how many layers are present here? How many functions are composed? First x changed to ax plus b, then the square root function comes in, then the sine function comes in, and then the cosine. So, obviously, it is very well a case of chain rule. Let us see what we do if I start with y as cos of sine of root of ax plus b. Starting with the outer layer, that is of the cosine function, the derivative can be written as minus sine of root of ax plus b into derivative of sine of root of ax plus b. So, if you keep the reference of u as we did earlier, if sine of root of ax plus b was u, then you would have multiplied with the derivative of u with respect to x. So, we are going to cut short, we are not going to bring u and v in this method. Now, what is the next layer? Sine function. So, we differentiate the sine function with respect to root of ax plus b, and we get cos of root of ax plus b multiplied with the previous minus sine of sine root ax plus b into the derivative of the next function, that is root of ax plus b, which leads us to the next layer, which is square root. So, the square root derivative would give us 1 by 2 root ax plus b. Inner function is a simpler one, ax plus b, but not an insignificant. If you miss multiplying by a, the derivative is incorrect. And therefore, we have differentiated a function which was composition of 4 functions without bringing this u v assumption. One more question to firm it up for you. Find derivative of cos of x cube into sine square of x to the power 5 with respect to x. What you need to observe in this case is that there is a product involved in the function. So, chain rule is what we are discussing, but we can't neglect the presence of product and therefore, product rule. Recall this rule which we are going to use just now. Starting with our function called as y, dy by dx by product rule gives us sine square x to the power 5 as it is, derivative of cos x cube in plus cos of x cube into derivative of sine square x to the power 5. Now comes the use of chain rule the moment I differentiate cos of x cube. Starting with the outer layer, that is cos, I get the derivative as minus sine of x cube into derivative of x cube. Let us also take a look at the next term also before we complete the first term derivative. Here sine square x to the power 5, the outermost layer is of the square function. So, differentiating I would get 2 times sine of x to the power 5 into the base, the derivative of the base, that is derivative of sine of x to the power 5. Completing the differentiation, we get sine square of x to the power 5 into negative sine of x cube into derivative of x cube giving us 3x square. The second term, you need to just watch out for derivative of sine of x to the power 5, that is nothing but cos x to the power 5 into 5 x to the power 4, again applying the chain rule. What is left is now just a bit of simplification. If something simplifies, cancels, good, otherwise you do end up with a long expression like this as your final answer. I hope students, today's lesson has brought in a lot of clarity as far as the chain rule is concerned. Chain rule is one of the basic rules that will continue to be in use as we explore other techniques of differentiation in our future lessons. See you till then. Hello viewers, today we are going to discuss 2 special methods of finding the derivatives of implicit functions and also the inverse trigonometric functions. What exactly do we mean by implicit functions? So far we have been using functions of the form y equal to f of x, where we had y is equal to sine square 2x plus 1, or y equal to x cube plus 2x minus 1, or y is equal to under root 1 minus cos x by 1 plus cos x, and you could find their derivatives with the appropriate rule applied. Such functions where y is clearly expressed as a function of x are called the explicit functions of x. What happens in these cases? Can you solve y in terms of x? Can you express y as a function clearly written in terms of x? Perhaps as you look at each one of them, you will be able to say no. Such functions where there is a dependence of y on x, but y cannot be expressed explicitly in terms of x, we say that y is an implicit function of x. And today we are here to discuss the differentiation of implicit functions. How do I find dy by dx if I have an implicit function? In this case, the relation is sine square x plus cos square y is equal to 1. So, task is the same. I have to find the rate of change, that is the instantaneous rate of change of y with respect to x, but I cannot express y in language of x directly. What do? Let us demonstrate. Differentiate the relation with respect to x, we get derivative of sine square x plus derivative of cos square y equal to derivative of 1. So, we are differentiating both sides of the given expression. Derivative of sine square x is not a problem, but note that cos square of y is present, not x. So, this is where you have to watch out. Using the chain rule, I get the derivative of sine square x as 2 sin x cos x. We are interested now in understanding what would be the derivative of cos square y would be. Again, it is a composition. Outermost function is the square function, then cosine function, and then another function, that is y, which is a function of x present. Therefore, applying the chain rule, I get the derivative as 2 cos of y into the derivative of cos of y, and the right hand side of course is 0, because derivative of a constant is always 0. Further, this becomes same as 2 sin x cos x as it was plus 2 cos y, and now the derivative of cos y using chain rule is minus sine of y into the derivative of y with respect to x. From here, we will just now separate out what dy by dx is. Rearranging, you get dy by dx as sin x cos x upon sin y into cos y. So, chain rule actually plays a significant role in finding the derivatives of implicit functions. Let us consider one more problem and see if there are other things that you need to be careful with. We have the question which says find dy by dx if sine of x y, the product x y plus x by y is equal to x square minus y. Again, differentiating the relationship with respect to x, we get derivative of sine of x y plus derivative of x by y is equal to derivative of x square minus y. The first term, that is sine f x into y, gives us cos x y into derivative of x y, chain rule again, plus what happened here? What I have used is what you see, I read it as x by y. So, there is a clear presence of quotient rule. Right hand side is just 2x minus dy by dx. Work is still not over because I still have to finish the first term. Again, applying the derivative of x y with the help of product rule, I get cos of x y into y plus x dy by dx. The other terms remain the same. Our job was to find dy by dx. So, what you really need to do is to rearrange, rewrite this expression and separate out dy by dx, which will give rise to the final answer written here for you. I will leave the little bit of simplification in between for you to follow up with. So, we have the derivative of implicit functions evaluated using the chain rule. Wherever product and quotient rule present, they play a role. Let us continue with understanding how this and other facts that we have learned so far help us to find the derivatives of inverse trigonometric functions. Since we have a limitation of time, I am not going to discuss the proofs of these results, but these results are going to play a very important role in this discussion, and that is nothing but list of these results or formulas, as you may call them, which suggests that the derivative of sin inverse x is 1 by root 1 minus x square, and yes, there is a condition present on x for this derivative to be well defined. So, those branches, that conditions on x are stated along with. You definitely need to memorize these results. There are no alternatives for it, but the best would be if you sit and work out the proof using implicit differentiation only. Start with y equal to sin inverse x and see what x is, and then work out the proof from there. We will focus on the applications. So, if I have to find the derivative of y, where y is cos inverse of root x, with respect to x, what would one do? Again observe composition, 3 layers, no rather 2 layers. I have inverse, cos inverse and the square root function present here. Let us see what would happen if I have to find its derivative using chain rule. Do you think I can write directly as minus 1 by root 1 minus x into derivative of root x? What happened in between? Derivative of cos inverse root x with respect to root x by their formula would be minus 1 by root of 1 minus root x whole square. Isn't that so? That simplifies to be minus 1 by under root 1 minus x. And what is the derivative of root x? Nothing but 1 by 2 root x. That gives you the derivative of y with respect to x as minus 1 by 2 root x into root of 1 minus x. Let us take another question. Find dy by dx if y is equal to cot inverse of root 1 plus sin x plus root 1 minus sin x by root of 1 plus sin x minus root of 1 minus sin x, where x is between 0 and pi by 2. Now, one of the things that you must possibly realize as we go through this statement is that this is a very familiar function. Where did you see that? Remember, we worked on these functions in inverse trigonometric functions chapter and learned how to simplify them, how to write them in their simplest form. And in fact, that is what is going to take away the major part of our problem. Derivative would only be calculated once this function is simplified. Let us get down to doing that. Start with y, which is cot inverse root 1 plus sin x plus root 1 minus sin x upon root 1 plus sin x minus root of 1 minus sin x. What can we do? I can write that sin x as cos pi by 2 minus x all across. Why would one do that? Simply because 1 plus cos theta is 2 cos squared theta by 2 and 1 minus cos theta is 2 sin squared theta by 2. Therefore, 1 plus cos pi by 2 minus x simplifies to 2 cos square pi by 4 minus x by 2 and 1 minus cos x simplifies to be 2 sin square pi by 4 minus x by 2. What is this going to be same as? This is same as writing cot inverse of absolute value of cos pi by 4 minus x by 2 plus sin pi by 4 minus x by 2 and in the denominator the same expression with a negative sign in between. Now, why do we have modulus here? Because square root of a square depends on what a is. Is it going to be positive a or negative a? Depends on a in sense, if a is a positive quantity, then root of a square is going to be a. If a is negative, then root of a square is negative a. So, what do we know about cos pi by 4 minus x by 2 and sin pi by 4 minus x by 2? Are they positive or negative quantities? Remember, there was a condition on x. X is strictly between 0 and pi by 2. So, x by 2 is strictly between 0 and pi by 4. Do you think then we can say that cos and sin of pi by 4 minus x by 2 are both positive quantities, and therefore, y simplifies to be cos pi by 4 minus x by 2 plus sin pi by 4 minus x by 2 divided by cos pi by 4 minus x by 2 minus sin pi by 4 minus x by 2. Now, this is an expression which we have worked with a number of times and know that this can be rewritten as cot inverse 1 plus tan pi by 4 minus x by 2 upon 1 minus tan pi by 4 minus x by 2. In case you have forgotten, what we do is divide numerator and denominator by cos pi by 4 minus x by 2. This leads us to nothing but cot inverse of tan of pi by 4 plus pi by 4 minus x by 2, a very familiar expression. This results in nothing but cot inverse of tan of pi by 2 minus x by 2 leads to cot of x by 2. And see, our y is just nothing but x by 2. So, the derivative of y with respect to x is simply half. So, the task was to find the derivative, and that took not just more than maybe a second to do, but without the simplification it would not have been so convenient to find the derivative. In fact, it is mandatory that you first simplify the expression and then find the derivative. And so, in order to differentiate inverse trigonometric functions, you must perfect the inverse trigonometric functions chapter, and specifically the part where we discuss how to simplify a given expression before you start with the derivatives. Best of luck, work hard, and I will see you next time. Hello viewers, continuing with our series on continuity and differentiability, today we are going to discuss two special techniques of differentiation. One called logarithmic differentiation and the other which would help us to differentiate functions which are in the parametric form. Let us start with looking at some functions which you may not have come across earlier as in the methods of differentiation. Let us consider functions of the kind x to the power x, cos x raised to the power x, log of x raised to the power tan x. These are special class of functions which in general can be expressed as a function of x raised to the power a function of x. So far we have not learned any method of finding derivatives of such functions. And just in case you are thinking about using the formula x to the power n to differentiate x to the power x, then stop and understand that that formula, that is the derivative of x to the power n is n x to the power n minus 1, is applicable only if n is a constant, is any real number. In this case, the power is also a function of x. So, here we use logarithm to the base e to differentiate such functions. Now, what do you know about logarithmic functions? Let us just catch up with that. Logarithmic functions are defined for any b greater than 1 as functions which are defined on positive real numbers to the real numbers, and the rule is y results in log of x to the base b if b raised to the power y is same as x. So, there is definitely a relation between exponential functions and logarithmic functions. If you had spent a little more time on this, you would have recognized that they are inverse functions of each other. Along with that, there are several useful properties of logarithm which we will be using as we progress down to this method. These are very essential and these are the key to the process which is known as the logarithmic differentiation. So, do make a note of them. Along with that, what we also need is an understanding of what are the derivatives of log and exponential functions. So, here are results which are mentioned just directly without proofs in your textbooks as well, which says that the derivative of exponential function is exponential x, derivative of log x, and when I write log x as we, that is the mathematicians do, it is meant to be with the base e. So, derivative of log x is 1 by x, derivative of a raised to the power x is a to the power x log of a, and derivative of log x to any other base other than e. So, in this case base a is same as 1 by x times log a. These four results will of course play a role as we go along and use the derivatives of logarithmic functions and exponentials anywhere else as well. Let us demonstrate to you the method, the process which is known as logarithmic differentiation through a simple problem. Starting with find dy by dx if y is equal to log of x raised to the power tan x. So, we begin of course with our function which is y is equal to log of x raised to the power tan x. In order to make it possible for us to differentiate, we take logarithm, and of course, again I am emphasizing to the base e of both sides. So, I get log of y is equal to log of log x raised to the power tan x. This gets rewritten as tan x into log of log x. How? Again, if you had noticed, this was one of the properties listed in our earlier slide. Here we have log of p to the power n is equal to n times log p. This helps us to bring the power as a factor in this expression, and therefore, we are now ready to differentiate both sides with respect to x. I get the derivative of log of y with respect to x, derivative of tan x into log of log x. This needs to be looked at with care, that when you differentiate log of y, there is a presence of chain rule, because log y is composition of logarithmic function and y which is a function of x, whereas the right hand side is product of two functions. So, to differentiate the right hand side, you need the product rule, and therefore, what would be the derivative of log y 1 by y into dy by dx, whereas the right hand side will result as the application of product rule applied on tan x and log of log x. So, we get on differentiating 1 by y dy by dx equal to sec square x log of log x plus tan x, and note how we have differentiated log of log x. Again presence of chain rule, log derivative will give me 1 by log x. So, when I say log derivative, it is derivative of log x with respect to log x, and then chain rule requires that I multiply with the derivative of log x, which is 1 by x, and thus our dy by dx is ready. Taking y to the right hand side, I get log of x raised to the power tan x into sec square x log of log x plus tan x into 1 by x log x. Not much gets simplified in this case. So, obviously, we would not worry too much about the simplification. Let us take another question, and this is one of the very frequently tested question in the class 12 board exams. The question says find the derivative, that is dy by dx, where y is x to the power sin x plus cos x raised to the power x. Now, you can see that it is just the first question that we did earlier repeated almost twice, because both the terms are of the class where we have f of x raised to the power g of x. So, both the functions need log in order to get the differentiation done. But also remember that there is no rule which says that log of the sum is same as sum of the logs. So, what can one do? Simply start with u as x raised to the power sin x and v as cos of x raised to power x. Then your y becomes u plus v and dy by dx is du by dx plus dv by dx. That is exactly what we did in our previous question. So, I will leave this for you to complete yourself. Repeat the same process mechanically and you will be fine. Consider another application. Find dy by dx if y is equal to this big expression where we have a square root, I have a quotient and I have product in both numerator and denominator. A usual chain quotient product rule procedure will make the task quite tedious. So, this is another situation where we take help of log and its properties which help us rewrite this function, simplify it down and then we bring in differentiation. Starting with y, which is square root of x plus 1 into x minus 3 upon x minus 4 into 7 minus x into x plus 2. Taking log of both sides, we get log of y as log of the entire expression, and again using the properties that we have just displayed, it all simplifies to half of log of x plus 1 plus log x minus 3 and then minus, because now we are looking at log of m by n resulting in log m minus log n. So, the entire expression gets written either as the sum or difference of terms which are with log. Taking the derivative, I get 1 by y dy by dx is equal to half times of 1 by x plus 1 plus 1 by x minus 3 minus 1 by x minus 4 plus 1 by 7 minus x. Now, where did I get this plus from? Because I had log of 7 minus x. So, when I take the derivative, it will be 1 by 7 minus x into the coefficient of x, which is minus 1, and therefore, I get a positive sign there, minus 1 by x plus 2 as the derivative of log x minus 2, and your problem is done. You just have to now rewrite your dy by dx by transposing y to the other side and just complete by saying what that y was. So, this is one more application of using the log to find the derivative of a function, process known as logarithmic differentiation. Let us also consider something new which you have again not come across earlier. Functions which are in the parametric form. The functions which are in parametric form represents the equation of a curve by a pair of equations, where these pair of equation represents the coordinates of the point on the curve in terms of a certain parameter. In this case, for example, if I have x as cos t, y is equal to sin t, this represents nothing but parametric equation of a circle with radius 1. You do not believe that? Well, it is so. You are familiar definitely with x square plus y square equal to 1 as the Cartesian equation of a circle with unit radius. So, if you do square x and y and add cos square t plus sin square t is equal to 1. So, t changes and it generates the coordinates of the points which lie on the curve, and that is a way of representing a Cartesian equation in terms of parameter. We are interested in finding the derivative of y with respect to x, where both x and y are functions of a certain parameter, say t. Then in that case, dy by dx is nothing but dy by dt divided by derivative of x with respect to t. So, as t changes, we find the instantaneous rate of change of y and divide by the instantaneous rate of change of x, provided denominator is not 0. And we are fine to find then the derivatives of functions which are in the parametric form. Consider one application. If x and y are connected parametrically by the equations, x is a times theta minus sin theta, y is a times 1 plus cos theta. Find dy by dx. So, what do? You begin by first finding dx by d theta. So, derivative of a times theta minus sin theta is nothing but a times 1 minus cos theta. Similarly, derivative of y, you have practiced differentiation to a large extent right by now. So, you are expert at finding such derivatives. dy by dx is nothing but the quotient of these two derivatives in the order derivative y with respect to theta divided by derivative of x with respect to theta. One does expect you to simplify this expression a little more. In this case, a gets cancelled. Not only that, trigonometric identities help us to rewrite sin theta as 2 sin theta by 2 cos theta by 2, 1 minus cos theta as 2 sin square theta by 2. It all simplifies to be same as minus of cot theta by 2. That would be the derivative of y with respect to x, where x and y are parametric functions of theta. So, the derivative is also a function of theta, it is not the function of x in this case. So, today's lesson covered two interesting important techniques, one logarithmic differentiation and the other which just touched upon the derivatives of functions in parametric form. I hope this has helped you to clear your doubts. Now, it is up to you to open books, start practicing and get expert at both the methods. See you in our next lesson. Thank you.
Today, we study the motion of objects in one dimension, that is motion of objects which are moving in a straight path. Man has been fascinated by the observation regarding motion of planets, motion of birds in sky, motion of fishes swimming in water, or any object which moves around us. Lots of objects move around us. To have a scientific understanding of these motions of objects, let us begin simply with objects moving in a straight path. Consider an object which moves along a straight path like this. Now, when we say that an object is moving, it means its position must be changing with time. Now, to locate the position with reference to some object or some position, let us say we have the origin which is represented by O in the figure. Now, the object is at point P, at the location P at a given time t1. The object is at another position Q all along this line at time t2. Then like this, the object goes on changing its position with respect to time. Then we say change of position continuously with time, we say the object is moving. How do we describe the motion? Motion along a line. One of the things that we do is consider the object at position P, which has the position coordinate x1. What do you mean by position coordinate? The location of the point P with respect to the origin is uniquely represented by the quantity x1 in this direction. Similarly, position of Q is given by its position coordinate, which is x2. When position goes on changing with time, say in the interval from t1 to t2, the object's position has changed from position x1 to x2. Then the change in position, which is represented here as delta x, which represents x2 minus x1, has occurred in a time interval which is represented by delta t here, which is t2 minus t1. We define a quantity called average velocity for this interval, average velocity, as represented by V bar as delta x by delta t. So, the average velocity in the interval t1 to t2 is represented as x2 minus x1 by t2 minus t1. The unit of average velocity is simply meter per second in SI unit. For example, when we say an object is having 4 meter per second as its velocity, what we mean is in every second interval of time, the displacement is 4 meters. Let us represent the motion of this object as position, how position varies with time, position being indicated here. This is x position versus time graph. Now, here we represent its position at point P as its coordinate x1 here, time t1 here. Now, point Q has its x coordinate x2 and its time coordinate is t2. Now, the object has moved from point P to point Q. As a function of time, the variation is this. Please understand, when I have joined these points P and Q, I have drawn a graphical representation, not necessarily a straight line. The object is moving in a straight line, but the variation of position with respect to time may be a curve. Now, as here I have represented. The average velocity, how do we represent in the graphical form? You join this point P to Q on the curve by a straight line, as I have done here. Now, in the interval time interval t1 to t2, which is this interval, the object has changed its position from x1 to x2, which I represent it here as x2 minus x1 represents the change in the position, and in this has occurred in the time interval t2 minus t1. Now, x2 minus x1 we have called it as delta x. Now, in this triangle, the height is represented by delta x. T2 minus T1, which we have called the time elapsed, which is indicated as delta t here, is represented at the base. When we say average velocity, which is represented by V bar. Here we mean delta x by delta t. Look at the graph, that is the height of this triangle divided by the base of this triangle, which we call as the slope of this line p q. Slope of the line p q represents the average velocity in the interval t 1 to t 2. Let us look at another graph of the same motion represented by x versus time graph. Here I am not given the positions, but I have indicated certain time intervals, which is t 1, t 2, time interval is the same. Again t 3 and t 4 are two different timings, but the time interval t 3 and t 4, which is given by the interval t 3 t 4, is the same as delta t here. Also t 5 t 6, they are at different positions at different timings, the object has different positions, and in each of these intervals look at the graph. Say for example, t 5 t 6, the displacement is indicated by delta x 3. In the interval t 3 to t 4, it is indicated by delta x 2 in the graph. It is indicated by the displacement delta x 1 is indicated between the interval t 1 and t 2. In the same time intervals, note from this graph that the time intervals are same, but the displacement in each of these intervals are different. What we mean here is the velocity in the interval t 1 to t 2, average velocity, which I write it as v 1 bar, that is in the interval t 1 t 2, and average velocity in the interval t 2 t 3 t 4, which I have represented as v 2. The average velocity in the interval t 5 t 6, which I indicated here by v 3 bar, each one of them are different because the slopes of these are different. That is, if you take this triangle having the same base, but the heights are different. Heights have gone changing with time, that is delta x 1, delta x 2, delta x 3 are increasing for the same interval of time, but at different timings. What does it mean is the average velocity goes on changing. So, the position time graph, if it is a curve like this, the average velocity go on changing with time. Then can we expect, what kind of a graph do we expect for a position time graph of an object which is moving with constant velocity? Can you think? Look at this graph. Let us take same intervals of time at different timings, which I am marking here on the graph. Look at this graph, the delta x in different intervals look at the delta x 3 in the interval t 5 t 6, t 3 t 4, look at delta x, which is given by this, represented by the height, which I have indicated delta x 2 here. Between t 1 t 2, the interval is the same, but timings are different. Look at this delta x 1. Do you see that in this case, when position time graph x versus t graph is a linear graph, it means the average velocity, that is delta x 1 by delta t 1, which is same as delta x 2 by delta t 2 for the same interval, delta t 1 being equal to delta t 2 is also equal to delta t 3. In that delta x 3, delta x 2 and delta x 1, they are all same. So, we say that this is a graph which represents average velocity is same and it is constant, unlike this graph which we did earlier. Look at this, this is a curve where the position time graph had different slopes at different timings. The slopes go on increasing means the velocity goes on increasing. Look at this graph again, where position versus time was a linear graph. We notice that the slope delta x 1 by delta t 1 is the same as delta x 2 by delta t 2 is the same as delta x 3 and delta t 3. The slopes are same, that is the height to base ratio is the same, and this is a straight line. What it means is the velocity does remain constant. Let us review what we have done in terms of how to analyze the motion, whether it is an object is moving at a constant velocity or varying velocity. Let us see, let us look at this graph, position x versus time. If the graph has a variation like this, look at point P. In the interval around this, the slope, that is delta x by delta t, is positive. Look at this interval where delta x variation is not there. There is a variation of delta t during the same interval. What does it mean? When there is no variation, the height is 0. So, it means this is the position in this time interval, the average velocity is 0. Let us look at this position again, where if I take the same interval, delta t represented being same, but at different timings the slope is different. It means in this kind of a nonlinear variation of x versus t, we come to the conclusion that average velocity goes on changing with time. Now, we are talking only about average velocity, that is velocity. When you say an object is between, example, if you say that an object is having a average velocity of 4 km per hour or 40 km per hour, whatever it is, when we say, you should specify the interval over which the average velocity is there, otherwise it has no meaning. What do you mean by when we say the car is moving at 40 kilometers per hour? How can car move at a certain instant of time? How can it have a velocity? We have said, when we talked about average velocity, we said there is a certain interval of time where we measure the change in position and the time interval over which, and we said average velocity is defined over an interval of time. What do you mean by instantaneous velocity? Look at this position time graph again, x versus t. The object is at a point P at a certain interval, and let us indicate it as x 1 as the position coordinate at time t 1. What do we mean by at point P, what is its velocity, or what is its velocity at time t 1? What do we mean by this? Now, how do we determine this? Does it make any sense at all? Let us look at the variation of this position coordinate of this object, which has been given like this. Now, when we say the velocity at average velocity, let us try to find out the average velocity. How do you find out the average velocity? Let us take a certain interval of time, say at time before this and at time little afterwards. Let us call this as a small interval of time, and if we indicate it here, that is t 1 minus a certain amount of time and t 1 plus certain amount of time. Now, here I find out what is called as change in position in that small interval of time, which I represent it as delta x and call it as delta x by delta t, but please note this t delta t is smaller. You make it still smaller. Around this point, take 2 points very close by, make this very small, that is delta t, in this case delta x, again you find out delta t, but this delta t being smaller than the earlier one. Go on doing this. Now, what we mean by instantaneous velocity at a certain time, which is represented by v, we mean delta x by delta t for small intervals of time, when which we indicate delta t tending to 0. We are trying to find out the value of delta x by delta t when delta t tends to 0, and in the graph, if this is the slope, then you make the interval smaller and smaller, then you draw a line and it becomes a tangent, and the slope of the tangent is what we mean by v instantaneous velocity. Slope of a tangent drawn to the curve at point P, but whatever be the point, that gives the instantaneous velocity. So, what we have done today is to define average velocity as velocity in an interval of time, that is change in this position coordinate, which we have called it as displacement. Displacement over an interval of time rate of change of displacement, that is delta x variation with delta t. Delta x by delta t we have called it as average velocity. What is instantaneous velocity? Instantaneous velocity is average velocity over a very, very small interval of time, which we call it as instantaneous velocity. The average velocity and instantaneous velocity are two different things. Average velocity is over an interval of time, whereas an instantaneous velocity is at a certain instant of time, which is found by drawing the slope of a tangent at a given point, whereas average velocity is measured by finding out the slope of the chord or the secant that is drawn between 2 points. In the next class, we will see how variation of velocity with time is to be understood in terms of a quantity called acceleration. I am Prabhakar. We will be discussing motion of objects in one dimension. That is, man has been fascinated by movement of objects, whether it is of planets in the sky or birds in sky or fishes in water or any vehicle which is man made. To understand the motion of objects, we will begin with motion of objects moving in a straight path. Consider point O, which is a reference, and I am trying to indicate a straight path along this line. Now, anything that moves in here changes its position. Let us say the position is at x at time t. Now, when we say the object is moving, what we mean actually is its location with reference to a certain point, which I have indicated here as origin, varies with time. That is, position, variation of position with respect to time is generally called as motion. In one dimension, x should vary with time. Consider, for example, a situation like this, which I am going to present. This is variation of position with time. T is given in seconds, x is given in meters. Say, for example, at t is equal to 0, it is at position 10 meters from the origin. T is equal to 1 second, it is at a position of 15 meters. Like this it goes on. Now, if you look at this data, x is continually changing with respect to time. We say, let us analyze this motion. Now, to look at this, I will plot the variation of position with respect to time, which I call it as position time graph. Look at the variation of position with respect to time of the data that I gave. Now, t is equal to 0 seconds, the position of the object is 10 meters. At t is equal to 1, it is at 15. At t is equal to 2, this is the kind of a plot that I have done, and it has been done from time t is equal to 0 to time t is equal to 11 seconds. Look at this graph carefully. What do you observe in this graph? The position variation with respect to time is what is indicated. Now, at t is equal to 6 seconds, the position is 28. Till 0 to 6 seconds, the position goes on increasing. Afterwards, what is happening? The position is decreasing. What does it mean? It means, if you look at the x coordinate, it is moving along a straight line and it is coming back towards the origin. That is all it means. See, at t is equal to 7 seconds, it is at 27.5 meters, whereas at t is equal to 10 seconds, it is at 17 meters. It means it is going along a straight line till t is equal to 6 seconds, then started moving backwards. That is, x goes on decreasing with t after it has reached the maximum position. Now, this variation of position with respect to time is measured in terms of a quantity which we define as average velocity. what is average velocity. Look at this graph again. The position of the object goes on changing with time. It starts from t is equal to 0, at t is equal to 0 it is at 10 meters, increases its position from the origin up to t is equal to 6 seconds. Then it starts moving backwards along the line, in the same line, till say at t is equal to 10 seconds it comes to a certain other position, which is lesser than what it started with. Now, I told you we will define a quantity called average velocity. Average velocity is defined as V average as the change in position. Say for example, it is at position x 2 at time t 2 and it is at position x 1 at time t 1, then we define a quantity called x 2 minus x 1 divided by t 2 minus t 1, which we call it as average velocity. Let us look at some portion of the graph which I am indicating here. At time t 1, the position coordinate is x 1. At time t 2, the position coordinate is x 2. The positions are indicated as p and q here in this graph. Now, it means the position has changed from time t 1 to t 2 in the time t 1 in the interval time from t 1 to t 2. The position has changed from x 1 to x 2. If I join this point p and q by a straight line p q and then draw a line parallel to the time axis, which is indicated here as p r, q r gives you change in displacement in the interval t 2 minus t 1. The slope of this line p q is defined as q r by p r. Here it is x 2 minus x 1 divided by t 2 minus t 1. We call this as the slope of this line p q, which is joining the points p and q along the curve. Now, in terms of the graph, what we mean by average velocity is delta x by delta t, which is nothing but the slope of the graph. So, slope of position time graph gives you what we call as the average velocity between the points p and q or between the interval time t 2 and t 1. So, delta x, which is the change in position coordinate, divided by the time interval, for this we define it as average velocity. Having defined average velocity as delta x 2 minus x 1 by t 2 minus t 1, which can also be written as change in position coordinate delta x, change in time coordinate, which is delta t. Let us try to calculate how is this average velocity is changing at different time intervals. Let us take for example, let us put time t 1 as 0 seconds. At time t 1 0 seconds, the position coordinate corresponding to it is 10 meters. At time an interval of say 2 seconds, at time t 2, which is 2 seconds, the position coordinate from the data is 20 meters. So, in the interval 0 seconds to 2 seconds, the average velocity is given by say 20 meters minus 10 meters, 2 seconds minus 0 seconds, which happens to be 5 meter per second. The average velocity in the interval 0 to 2 seconds happens to be 5 meters per second. Do the process, let us say, for another time interval between 2 seconds to 4 seconds. Let us do that again. Say now t 1 happens to be 2 seconds, x 1 happens to be 20 meters, t 2 happens to be 4 seconds and x 2 happens to be 25 meters. In this interval, V average turns out to be, if you substitute the values, 25 minus 5 is the change in the position coordinate, which we call as the displacement. This delta x is called as displacement, and this is the displacement in the interval 4 seconds to 2 seconds. So, the change in displacement per unit time here happens to be 5 meters per 2 seconds, which happens to be 2.5 meters per second. Change in position coordinate, we are calling it as displacement. So, V average in this case happens to be 2.5 meters per second, whereas in the earlier interval between 0 to 2 seconds, it happened to be 5 meters per second. Let us do this average velocity calculation for another interval of time between, say, t is equal to 4 seconds, t1 is equal to 4 seconds to t2 equal to 6 seconds. Now, from the data that we have, at time t1 its position coordinate happens to be 25 and x2 happens to be corresponding to 6 seconds happens to be 28. Let us calculate the average velocity in the interval t1 4 seconds and t2 6 seconds, that is the interval between 4 seconds and 6 seconds. The position at t1 is equal to 4 seconds, the position coordinate corresponding to that is 25 meters, and at t is equal to 6 seconds, the position coordinate happens to be 28 meters. Now, the V average in this case, if you substitute in the equation x2 minus x1 divided by t2 minus t1, which I am writing it as delta x by delta t, for this happens to be, say, 28 meters minus 25 meters, which happens to be 3 meters, and the delta t happens to be 2 seconds. The V average happens to be 1.5 meter per second. In all these cases, you realize from the data that we have given you, what we have calculated is that the average velocity goes on changing with time. Let us refer to this position time graph. Let us have a relook at it again. Now, in the interval 0 to 2 seconds, the displacement happens to be 10 meters. In the interval 2 to 4 seconds, it is becoming smaller. In the interval between 4 and 6 seconds, it is still getting smaller. If you want to look at this, how do we look at the slope of the graph? Slope of the graph is the point joining these two, and that is the straight line, and this is delta t and this is delta x. This is delta x and this is delta t, and in the interval 0 to 2 seconds, this is the slope of the line joining these 2 points. In the interval 2 to 4 seconds, let us join this and find the slope again in the interval 2 to 4. That is change in position coordinate by the change in time interval. Again between 4 and 6 seconds, let us do that again in the graph. Look at this. For the same time interval, change in position coordinate is becoming smaller and smaller. It means the slope of the graph is changing. Now, slope of the graph, if you look at this, the line that is joining here, these makes a certain angle, and the slope of this line is delta x by delta t. Now, in this graph, the slope goes on changing, but now look at this, when it goes on after say 6 seconds, between 8 and 10 seconds, 6 to 8 seconds. Now, if you look at the 6 to 8 seconds, the slope is negative. What do you mean by slope is negative? Look at this. Now, x2, this is at time t is equal to 6 seconds, this was the position. At time t is equal to 8 seconds, the position has decreased. Its position has come down, say, from a certain level, which is 28, and it has come to 26 or so. In that case, look at this. This was x1, this is x2, x 1 is greater than x 2. As time goes on increasing, the position goes on decreasing. In that case, delta x by delta t happens to be negative. Means after 6 seconds, the average velocity is negative. What do you mean by negative velocity? In negative average velocity, from 0 to 6 seconds, the velocity, average velocity was positive. That is, till 0 to 6 seconds, the average velocity was changing, but it was remaining positive. But after 6 seconds onwards, till 10 seconds, the slope of the graph is negative, because at the final position coordinate, it is less than the initial position coordinate as time goes on increasing. It only means it was going along the x axis, reached at time t is equal to 6 seconds, it reached the maximum position, then it reverses its direction of motion. When we say the average velocity is negative, it means during that velocity being positive, average velocity being positive, it was moving in one direction. When you say it is negative, it is moving in the opposite direction. Let us summarize what we have learned today. When an object is moving along a straight path in a certain direction, we defined an average velocity, and considering as x increases with time, in that sense the average velocity will be increasing, changing. But when average velocity decreases, it means if it becomes negative, when you say it is negative, it means it is moving in the opposite direction. That is, during that interval the displacement is decreasing. In the next session, we will be talking about the velocity at an instant of time. I am Prabhakar. We will be talking about instantaneous velocity of an object moving in a straight path. Consider an object moving along a straight path like what I am indicating here. Let us say it starts, the origin is O, the reference point, and its position coordinate x varies with time. Then how do we define instantaneous velocity of this object moving along a straight path? Let us look at this graph, position time graph, in a very small interval of time, that is from time t to t plus delta t of the particle moving along a straight path. Its position coordinate at time t is x, at time t plus delta t is x plus delta x. Now, to find the average velocity in the interval t and t plus delta t, what we do is you join this point P to point Q and you get this line. Now, in the interval t and t plus delta t, that is the time gap being delta t, the change in position is given by delta x in the figure, which is shown as delta x. The time interval is delta t, which is indicated. Now, this delta x is the height of this triangle and delta t is the base of this triangle. Delta x by delta t is the ratio of the height to the base of this triangle, which is found by the line p q. The value of delta x by delta t is generally called average velocity. Now, look what I am going to do is to reduce this time interval between t and t plus delta t. Consider an interval of time which is smaller than this. At that instant of time, the particle is object is at q1, q dash. Join the line p q dash and form the triangle, the right angle triangle p q1 r1 or p q dash r dash, whatever it is. Now, delta x dash is the height of this triangle and delta t dash is the base of this triangle, and the line that is p q dash, the slope of this line is delta x dash by delta t dash, which is average velocity in that interval of time delta t dash. You reduce this time gap smaller and smaller and then ensure that you make it almost 0, then in that case the slope of this graph goes on increasing, and at point P when you make delta t almost tending to 0, you draw a line which is called the tangent line at the point P, and the slope of this line is called the instantaneous velocity. The slope of the line at P, that is V, which is the slope of the tangent at point P, is written as limit of delta x by delta t tending to 0, is called the instantaneous velocity at point P. This is instantaneous velocity. When we say instantaneous velocity, it is limit of delta x by delta t as delta t tends to 0, which is nothing but if the slope of the tangent that is drawn at that instant of time of the x position time coordinate graph. So, V is called rate of change of displacement, because delta x is a measure of the displacement, and time rate of change of displacement at a given instant of time is called the velocity at that instant. When we say instantaneous velocity, we write it as V is limit of, that is change in position coordinate, which we have called it as delta x, which is nothing but displacement per unit time when the time interval is very, very small. So, we write V is equal to limit of delta x by delta t as delta t tends to 0. In other words, in the language of mathematics, this is indicated as dx by dt. They mean the time variation of position with respect to time variation of position, that is rate of change of x with respect to dt t, which they write it as differential of x with respect to time. So, velocity is nothing but rate of change of position with respect to time. This is instantaneous velocity. Now, let us look at another position time graph, that is change of position with respect to time, that is x t graph. Now, look at this graph. The position is continually changing, the object is moving in a straight path, but the displacement, the change in position is indicated along the curve. Can you find out the instantaneous velocity at P, instantaneous velocity at Q, or instantaneous velocity at R? Can you compare the instantaneous velocities? Now, look at this. How do we do? If you draw a tangent to the curve at this point, which I am indicating like this tangent has a slope which is given by delta x by delta t and very small interval of time, and this happens to be, this slope of this tangent happens to be a positive slope. If I draw a tangent to the curve at point Q, the tangent line touching this curve at only one point, and this is 0 slope. Look at this point R. If I draw a tangent that almost coincides with the curve, this slope of this tangent is negative. It means at point P, the object has positive velocity, the object has 0 velocity at point Q, at point R the object has negative velocity. When the object has positive velocity, it means whatever you have defined as positive direction, the object will be moving along that direction. When you have negative velocity, it means the object will moving against the original direction, which you have called it as positive. It means the object, in this case, in the case of an object moving in a straight line path, the object is trying to come back, is coming back or moving in the opposite direction. The velocity direction, the direction of velocity, when you say it is positive, it is along the moment. When you say the velocity is negative, it means the object is moving against the direction in which it was originally moving, or the object is trying to retrace. When you say the object is at rest instantaneously, that is at q, its instantaneous velocity is 0. The object is continually changing its position, but at some point of time its velocity could be 0, after that it could be negative, it could be positive. So, an object moving in a straight line path will consider the velocity variation with time. Look at this graph which I have presented, which shows the variation of velocity with respect to time. We will discuss about the variation of velocity with respect to time in the next session with the idea of what is meant by acceleration of an object moving in a straight line. I am Prabhakar. Today, we will introduce the concept of acceleration of an object moving along a straight path. Now, look at this. In the figure, I have indicated a straight line with an arrow and O as a point of reference. Now, the data that I have for this motion is velocity as a function of time, that is instantaneous velocity in meters per second as a function of time. You have at time 0 the velocity is 10 meters per second, at time 4 seconds it is 23.5 meters per second, at 8 seconds it is 17 meters per second, at 10 seconds it is 6.5 meters per second. Now, the data of velocity as a function of time is plotted in the graph. Please look at this graph, velocity time graph. At t is equal to 1 second, the velocity is 15 meters per second. At 4 seconds, it is 23.5 meters per second. At 8 seconds, it is 17 meters per second. The velocity goes on changing with time. The velocity is increasing during a certain interval up to 5. Afterwards, the velocity goes on decreasing. What does this mean? Velocity as a function of time has a variation, but is that variation constant? How does it vary? Let us try to find out how this velocity variation with time is expressed in physics. The variation of velocity with respect to time is shown here. Look at this graph. At time t1, the velocity is v1, at time t2, the velocity is v2. The variation in the velocity in the interval t1 to t2 is measured by joining this point p and q, that is where the velocities are v1 and v2. Join this line from p to q and construct this triangle. The height of this triangle is v2 minus v1 and the base of this triangle is t2 minus t1. The slope of this line p q is called the average acceleration. Average acceleration in the interval time t1 to t2 is defined as change in velocity, that is v2 minus v1 divided by t2 minus t1, which is represented as delta v by delta t. So, the average velocity in the interval is defined as delta v by delta t in the interval t1 to t2. Now, having defined average acceleration as change in the velocity in the interval delta t, let us do the calculation for some of the average acceleration cases. In the interval say 0 to 2 seconds, let us take t1 as 0 seconds and t2 as 2 seconds. The velocity corresponding to t1 0 seconds is 10 meters per second and the velocity corresponding to the time t2 is equal to 2 seconds is 18 meters per second. In this interval of time, the average acceleration in the interval 0 to 2 seconds is 18 meters per second minus 10 meters per second, which is 8 meters per second is the change in the velocity in the interval 0 to 2 seconds, that is 2 seconds. So, the average acceleration is 4 meters per second per second. An average acceleration in the time interval between t is equal to 6 seconds and that is t 1 is equal to 6 seconds to t 2 is equal to 8 seconds. At t 1 is equal to 6 seconds, the velocity is 23.5 meters per second and velocity at time t 2 corresponding to 8 seconds is 17 meters per second. Now, average acceleration in this interval of time is v 2 is 17 meters per second, v 1 is 23.5 meters per second. So, v 2 minus v 1 is minus 6.5 meters per second, and that is the change in the velocity in the interval from 6 seconds to 8 seconds, the interval being 2 seconds. So, the average acceleration is minus 3.25 meter per second per second. Just like velocity, acceleration can be positive or negative. The average acceleration can be positive or negative. What do you mean by average acceleration being positive or negative? Now, look at this data. The acceleration, the average acceleration is a measure of how the velocity is changing. Now, in the interval 0 to 6 seconds, the velocity reaches its maximum value at t is equal to 4, that is 23.5 meters per second, and in the next interval from 6 seconds to 10 seconds, the velocity is decreasing. It means the average acceleration in the interval 0 to 5 seconds is positive. After that, the velocity average acceleration in the interval from t is equal to 5 seconds to 10 seconds is decreasing. The average acceleration can be positive, negative or 0 depending upon the average acceleration happens to be positive when the velocity is increasing with time. The average acceleration in a certain interval of time happens to be 0 when the velocity does not change with time. The acceleration average acceleration happens to be negative or becomes negative when the velocity decreases with time. Having studied what average acceleration means, let us move to the idea of instantaneous acceleration. Now, look at this graph where the velocity has been plotted as a function of time for very small intervals of time. The object has velocity v 1 at time t 1, which is indicated as point P. The velocity at time t 1 plus delta t is indicated at point Q corresponding to a value v 1 plus delta t v 1 plus delta v 1. Average acceleration in the interval t 1 to t 1 plus delta t is given by the slope of the line joining point P to Q, that is velocities at t 1 and velocity at t 1 plus delta t, which is indicated in the graph as the line P Q. The average acceleration here is indicated by this delta v corresponding to the height of this triangle and this base which is delta t. The average acceleration for this small interval of time is delta v by delta t. You make this smaller and smaller, the time gap is made smaller and smaller. Let us look at this point q 1. Now, the time, if you look at the time interval, this is lesser than t plus delta t, which we considered earlier. Now, look at this line p q 1, the slope of this line is larger as the height is larger and the base is smaller, or the breadth is becoming smaller of this triangle. Now, look at the triangle which is formed by p q 2, that is the delta t is being reduced and the height goes on increasing. it means the point Q, if it comes very close to this point P, then you get a tangent to this curve at point P, then you have the tangent line. The slope of the tangent line, that is the height to the base formed by the tangent line, is called the instantaneous acceleration at point P. So, instantaneous acceleration at point P is the slope of the tangent line at P. That is how the instantaneous acceleration is defined. Average acceleration has been defined as rate of change of velocity in a certain interval of time. Instantaneous acceleration is limit of change in velocity, which is delta v by delta t, as delta t is made very small, almost tending to 0. The average acceleration, which is indicated here as a bar or written as a average with subscript, is change in velocity in a certain interval of time, which is delta t, or a average is read as delta v by delta t. Instantaneous acceleration, a, is written as change of velocity with respect to time over a very short interval of time, very small interval of time, where the interval of time is almost becoming 0. So, average acceleration over a very small interval of time is called the instantaneous acceleration at a given point in time. In the next unit, you will study the relationship between acceleration, displacement and velocities at various intervals of time.
I am Mrs. Roma Malik and I will be teaching class 11th biology, unit Diversity in the Living World, the chapter Biological Classification. Now, what is biological classification? It is the scientific procedure of arranging organisms into groups and subgroups on the basis of their similarities and dissimilarities and placing the groups in a hierarchy of categories. It was first proposed by Aristotle based on morphological characters. Linnaeus further classified them into two kingdoms, Plantae and Animalia. R. H. Whittaker proposed a 5-kingdom classification: Monera, Protista, Fungi, Plantae, Animalia. We will be discussing these kingdoms one by one. Kingdom Monera. It is found everywhere and in extreme habitats. It is grouped under 4 categories based on their shapes: Cocci, which are the spherical ones; Bacilli, the rod-shaped ones; Vibrium, the coma-shaped; Spirilla, the spiral-shaped. They have metabolic diversity. They may be autotrophic, photosynthetic autotrophic, as well as chemosynthetic autotrophic. A vast majority are heterotrophs. It includes archibacteria and eubacteria. Archibacteria are found in harsh habitats. They are halophils. They are found in salty areas, thermoacidophils, that is in hot springs, and methanogens in marshy areas. They have different cell wall structure which helps their survival in extreme conditions. Eubacteria, they are the true bacteria. They have a rigid cell wall. Cyanobacteria, Nostoc, Anabina are all included under this. Cyanobacteria has chlorophyll A. They are photosynthetic, autotrophs, unicellular, colonial, filamentous, marine or terrestrial. Nostoc and Anabina, they can fix atmospheric nitrogen in specialized cells called heterocyst. They have a mucilage sheath around their colony as well. The heterotrophic bacteria act as decomposers. They are also responsible in the preparation of curd from milk. They are able to fix nitrogen and helps in the production of antibiotics. Some of them are pathogens. They damage human beings, farm animals as well as other organisms. Reproduction is by fission, and under unfavorable condition it is by spores. Kingdom Protista, they are single celled eukaryotes which includes chrysophytes, dinoflagellates, euglenoids, slime molds and protozoans. Chrysophytes, they are the diatoms and golden algae. Their characteristics are they are found in fresh water and marine. They are photosynthetic. Cell wall forms two thin overlapping shells. Their walls are embedded with silica. They are the chief producers in the oceans. Dinoflagellates, they are mostly marine and photosynthetic. Cell wall has a stiff cellulose plate. Presence of two flagella. Rapid multiplication makes the sea appear red, which is referred to as red tides. At times, they multiply rapidly and make the sea toxic, which makes the survival of other marine animals very difficult. Euglenoids, they are freshwater organisms. Instead of cell wall, they have a pellicle. Presence of two flagella. They are photosynthetic in the presence of sunlight, but in the absence of sunlight, they behave as heterotrophs. Slime molds, they are saprophytic. Under suitable conditions, they form plasmodium, which is an aggregation of cells, and under unfavorable conditions, the plasmodium differentiates, forming fruiting bodies bearing spores at their tips. Protozoans, the protozoans may be amoeboid protozoans, flagellated protozoans, ciliated protozoans and sporozoans. The amoeboid protozoans have pseudopodia, with the help of which they carry out their locomotion. Flagellated protozoans have flagella, example trypanosoma. Ciliated protozoans have cilia, example paramecium. And the sporozoans, they are diverse organisms, have an infectious spore-like stage in their life cycle. Example, plasmodium, which brings about the disease malaria. Kingdom fungi, they are heterotrophic. They may be saprophytes, parasites, symbionts when they are found in association with algae, mycorrhiza when they are found with the roots of higher plants. Reproduction, reproduction may be by vegetative means, which is by fragmentation, fission and budding. Asexual reproduction may be by spores, conidia, sporangiospores or zoospores. Sexual reproduction is by the oospores, ascospores and basidiospores. The sexual cycle follows three stages: plasmogamy, karyogamy and meiosis. Plasmogamy is the fusion of protoplast. Karyogamy is the fusion of nucleus, which results in the formation of zygote. This zygote then undergoes meiotic division and forms haploid spores. Phycomycetes, example mucor and rhizopus. They are found in aquatic habitats, decaying woods and moist places. Their mycelium is aseptate and cenocytic. Asexual reproduction is by zoospores or aplanospores. Sexual reproduction: isogamous, anisogamous, oogamous. Ascomycetes: they are the sac fungi. Example: yeast, Penicillium aspergillus. They are saprophytic as well as parasitic. They are decomposers as well as coprophilous. The mycelium is branched, septate. Asexual spores are the conidia, which are exogenously borne. The sexual spores are the ascospores, which are endogenously produced in sac-like asci. Their fruiting bodies is known as ascocarp. Basidiomycetes: example, mushroom fungi. They are found in soil, logs and tree stumps. Mycelium is branched and septate. Asexual spores are absent. Vegetative reproduction takes place by fragmentation. The fruiting bodies formed is known as basidiocarp. Deuteromycetes: it is also known as imperfect fungi. Example, Alternaria. They reproduce by asexual spores called conidia. Their mycelium is septate and branched. They may be saprophytes or parasites. They are the decomposers of litter and help in mineral cycling. Kingdom Plantae: they are eukaryotic chlorophyll containing organisms. Few partially heterotrophic. Example, the insectivorous plants, the Venus flytrap, and parasites, the Cuscuta. The cell wall is made up of cellulose. Plantae includes algae, bryophytes, pteridophytes, gymnosperms and angiosperms. Life cycle has two distinct phases: diploid sporophytic and haploid gametophytic. The diploid sporophytic and haploid gametophytic alternates with each other, and so this pattern of life cycle is known as alternation of generation. Kingdom Animalia: they are heterotrophic, eukaryotic, multicellular organisms. They lack cell wall. Holozoic mode of nutrition, definite growth pattern, presence of sensory neuromotor mechanism. They are capable of locomotion. Sexual reproduction is by the copulation of male and female, resulting in embryological development. In the 5 kingdom classification, the acellular organisms are not mentioned, but there are certain acellular organisms like virus, viroids and lichens. Virus: the word virus means venom or poisonous fluid. They are non-cellular organisms. They are nucleoprotein and the genetic material is either DNA or RNA. The protein coat is called capsid, which is made up of capsomeres, which are the subunits. The diseases which are brought about in animals are mumps, smallpox, herpes, influenza and AIDS. The plant diseases brought about by viruses are mosaic formation, leaf curling and rolling. Viroids: they are smaller than virus. They have free RNA and lack protein coat. RNA has low molecular weight. Lichens: they are the symbiotic association between algae and fungi. The algal component is known as phycobiont and the fungal component is known as mycobiont. The relationship is known as symbiotic relationship. They are very good pollution indicators. Biological classification is essential in knowing the cell structure, body organization, mode of nutrition, reproduction and phylogenetic relationship. Let us have a quick recap of the portions we studied. Kingdom Monera, Archibacteria, Eubacteria. Under kingdom Protista, we studied chrysophytes, dinoflagellates, euglenoids, slime molds, protozoans. Under kingdom Fungi, Phycomycetes, Ascomycetes, Basidiomycetes, Deuteromycetes, and the kingdom Plantae and Animalia. We will continue with the same unit in the next episode.
साहब ने, कबीर साहब ने इस भजन के माध्यम से लोगों को ये संदेश दिया है कि ईश्वर किसी एक जगह पे महफूज होने की चीज नहीं है। परमात्मा किसी मंदिर मस्जिद की चार दीवारी में कैद होने की चीज नहीं है। परमेश्वर हर जगह मौजूद है। ये तो सिर्फ एहसास की चीज है, उसकी उपस्थिति ये हमें समझने की बात है। ये भजन के पहले साहब के ही वाणी में 4 पंक्ति। या घट या घट या घट, या घट भीतर 7 समंदर, या ही में नदी और नारा। या घट भीतर काशी द्वारिका, या ही में ठाकुर द्वारा। इसी घट में सब कुछ मौजूद है। या घट भीतर चंद्र सूर्य है, या ही में 9 लाख तारा। कहत कबीर सुनो भाई साधो, या ही में सिरजनहारा। या ही में सिरजनहारा। यही सब कुछ है। मुझे कहां ढूंढता है? मुझे खोजने की आवश्यकता नहीं है। मैं मौजूद हूं तेरे पास। मुंह को कहां ढूंढे रे बंदे, मैं तो तेरे पास में। मुंह को कहां ढूंढे रे बंदे, मैं तो तेरे पास में। मुंह को कहां मैं तो तेरे पास में। ना मैं मंदिर ना मैं मस्जिद, ना मैं मंदिर ना मैं मस्जिद, ना मैं मंदिर ना मैं मस्जिद, ना मैं मंदिर मस्जिद। साहब की इस पंक्ति से मुतासिर हो करके किसी एक शायर ने ये बात कही है, इधर मंदिर इधर मस्जिद, इधर गुरुद्वार इधर गिरजा। इधर मंदिर इधर मस्जिद, इधर गुरुद्वार इधर गिरजा। तुझे इबादत से मतलब है, जिधर चाहे उधर गिरजा। ना मैं मंदिर ना मैं मस्जिद, ना मैं मंदिर ना मैं मस्जिद, ना मैं मंदिर पहले बंद में साहब ये संदेश देना चाह रहे हैं, मैं किसी जप तप या उपवास में या किसी कठिन व्रत में मिलने की चीज नहीं हूं। मुझे सहज पा सकते हो सच्ची भावना से। ना मैं जप में, ना मैं तप में, ना मैं व्रत उपास में।
ना मैं जप में, ना मैं तप में, ना मैं व्रत उपास में।
ना मैं जप में, ना मैं तप में, ना मैं व्रत उपास में।
ना मैं जप में, ना मैं तप में, ना मैं व्रत उपास में।
ए ना तो कोनो क्रिया कर्म में,
ना तो कोनो क्रिया कर्म
हो
में,
ना तो कोनो क्रिया कर्म में,
ना तो कोनो क्रिया कर्म में।
ना ही जोग संन्यास में।
मोको कहाँ ढूंढे रे बंदे, मैं तो तेरे पास में। मोको कहाँ ढूंढे रे बंदे, मैं तो तेरे पास में।
ना मैं मंदिर, ना मैं मस्जिद,
ना मैं मंदिर, ना मैं मस्जिद,
ना मैं मंदिर, ना मैं मस्जिद,
ना मैं मंदिर, ना मैं मस्जिद।
ना काबे कैलाश में।
मोको कहाँ ढूंढे रे बंदे, मैं तो तेरे पास में। मोको कहाँ ढूंढे रे बंदे, मैं तो तेरे पास।
मोको कहाँ ढूंढे रे बंदे, मैं तो तेरे पास में। मैं किसी प्राण पिंड इसके चक्कर में नहीं हूं। मैं कोनो गुफा में नहीं जो मुझे तलाश के लिए आप निकल जाएं। मैं हर जगह मौजूद हूं। मुझे खोजिए, मुझे एहसास करिए। ईश्वर वो चीज है। नहीं प्राण में, नहीं पिंड में, ना ब्रह्मांड आकाश में।
नहीं प्राण में, नहीं पिंड में, ना ब्रह्मांड आकाश में।
नहीं प्राण में, नहीं पिंड में, ना ब्रह्मांड आकाश में।
नहीं प्राण में, नहीं पिंड में, ना ब्रह्मांड आकाश में।
ना मैं भ्रुकुटी भंवर गुफा
ना
में,
मैं भ्रुकुटी भंवर गुफा में,
ना मैं भ्रुकुटी भंवर गुफा में,
ना मैं भ्रुकुटी भंवर गुफा में।
सब सांसों के सांस में।
मोको कहाँ ढूंढे रे बंदे, मैं तो तेरे पास में। मोको कहाँ ढूंढे रे बंदे, मैं तो तेरे पास में।
ना मैं मंदिर, ना मैं मस्जिद,
ना मैं मंदिर, ना मैं मस्जिद,
ना मैं मंदिर, ना मैं मस्जिद,
ना मैं मंदिर, ना मैं मस्जिद।
ना काबे कैलाश में।
मोको कहाँ ढूंढे रे बंदे, तेरे पास। मोको कहाँ ढूंढे रे बंदे, मैं तो तेरे पास में।
अंत में साहब कहते हैं, मुझे कोई खोजे श्रद्धा विश्वास के साथ में, प्रेम सद्भावना के साथ, तो तुरंत ही मिल जाए हम। मुझे एहसास तो करे मैं हर जगह मौजूद हूँ, जड़ चेतन में हूँ, जर्रे जर्रे में। खोजी हो तो तुरते मिल हो एक पल की तलाश में।
खोजी हो तो तुरते मिली हो एक पल की तलाश में।
खोजी हो तो तुरते मिली हो एक पल की तलाश में।
खोजी हो तो तुरते मिली हो एक पल की तलाश में।
कहीं कबीर सुनो भाई साधो,
कहीं कबीर सुनो भाई साधो,
कहीं कबीर सुनो भाई साधो,
कहीं कबीर सुनो भाई साधो।
ये सब सांसों के साथ में।
मोको कहाँ ढूंढे रे बंदे, मैं तो तेरे पास में। मोको कहाँ ढूंढे रे बंदे, मैं तो तेरे पास में।
ना मैं मंदिर, ना मैं मस्जिद,
ना मैं मंदिर, नाम है मस्जिद,
नाम है मंदिर नाम है मस्जिद,
नाम है मंदिर नाम है मस्जिद।
नाकामे कैलाश में
मुझको कहाँ ढूंढे रे बंदे, तेरे पास में। मुझको कहाँ ढूंढे रे बंदे, मैं तो तेरे पास में। मुझको कहाँ ढूंढे रे बंदे, मैं तो तेरे पास में।
मुझको कहाँ ढूंढे,
तेरे पास में।
मुझको कहाँ ढूंढे,
तेरे
मुझको कहाँ ढूंढे। ए जी सब दिन सुखा सुखा रे नदिया, एक दिन पूरा पूरा रे मोर बोले तंबूरा, मोर बोले तंबूरा। साहब की वाणी को हमारे छत्तीसगढ़ में कायाखंडी के रूप में प्रस्तुत करते हैं। ये जीवन 4 दिन की है और चले जाना है। कबीरा जब हम पैदा हुए, जग हंसे हम रोए, ऐसी करनी कर चलो कि हम हंसे जग रोए। साहब ये कहते हैं कि मोह माया से दूर हो जाइए, लेकिन मोह माया के बंधन से लिपटा हुआ आदमी जब आखिरी वक्त आता है तो उस समय भी यही कहता है कि इस मैहरवा में 2 दिन और रह जाएं, 4 दिन रह जाएं और फिर उसके बाद ले जाना ईश्वर। जाना दूर दूर दूर, रात अंधियारी, ये जी सर पे गठरी भारी, चोर खड़े मार्ग मां लूटे हो, ये जी कर ले जतन रखवारी। ए दिनचारी मैहरवा मां खेले लेते गो दिनचारी,
ओ दिनचारी मैहरवा मां खेले लेते हो दिनचारी।
ओ दिनचारी मैहरवा मां खेले लेते गो दिनचारी।
ए दिनचारी मैहरवा मां खेले लेते हो दिनचारी।
ए दिनचारी मैहरवा मां खेले लेते हो दिनचारी, मैहरवा मां
खेले लेते हो दिनचारी। दिनचारी मैहरवा मां खेले लेते हो दिनचारी। दिनचारी मैहरवा मां खेले लेते हो दिनचारी। दिनचारी मैहरवा मां खेले लेते हो दिनचारी।
साहब ने पहले बंद के माध्यम से ये कहना चाह रहे हैं, कोई काम नहीं आने वाला। जब अंतिम क्षण बुलावा आ जाएगा तो कोई काम नहीं आएगा, न भाई न भतीजा न बेटा न कोई काम नहीं आएगा। ना कामा ही भाई भतीजा ना कुरवन के पूता ओ पूता जी
जे 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 ओ जे 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 जे। ना कामाई भाई भतीजा ना कुरवन के पूता हो। जे 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 ओ जे 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 जे।
ये जी यही बुलावा परमेश्वर के,
आई बुलावा परमेश्वर के।
बुलावा परमेश्वर के, आई चतले गही दूता मैहरवा मां
खेले लेते हो दिनचारी। दिनचारी मैहरवा मां
साहब कहते हैं, अंत में 4 व्यक्ति आपको कांधे में ले करके शमशान में फूंक के आ जाएंगे, सारी बातें वहीं खत्म हो जाएगी। 4 गजे चर गजी कहावे, चढ़े काट के घोड़ा ओ घोड़ा जी 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 जी।
4 गजे चर गजी कहाए, चढ़े काट के घोड़ा ओ घोड़ा जी जी जी।
साहब के इस वाणी से हिंदुस्तान के मशहूर शायर जनाब जिया अंसारी साहब उनका एक ख्याल है, साहब से ये मुतासिर होकर के कहते हैं, मरने के बाद एक खता और करूंगा, मरने के बाद एक खता और करूंगा, पैदल चलेंगे लोग, मैं कांधे पे रहूंगा।
4 गजे चर गजी कहाए, चढ़े काट के घोड़ा ओ घोड़ा जी जी जी।
4 संत तोला बोहि के लगही,
4 संत तोला बोई के लगी,
4 संत तोला बोहि के लगही,
4 संत तोला बोई के लगी।
ए तोरे कमर के ढोरा मैया बाबा,
खेले लेते हो दिन चारी, दिन चारी मैहर मामा, खेले लेते हो दिन चारी, दिन चारी मैहर मामा, खेले लेते हो दिन चारी, दिन चारी मैहर मामा, खेले लेते हो दिन चारी, दिन चारी मैहर मामा, खेले लेते हो।
अंत में साहब सारी बातों की निचोड़ यहीं पे ला करके कह देना चाह रहे हैं कि सब कुछ यहीं खत्म हो जाएगा, सिर्फ ईश्वर का नाम रह जाने वाला है। हाड़ जरे तोर बन कस लकड़ी के सजरे बन घासा हाँ,
हार जरे तोर बन कस लकड़ी के सजरे बन घासा जी 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 जी।
ये सब जग जलता देख के रामा,
सब जग जलता देख के रामा,
सब जग जलता देख के रामा, भाई कबीर उदासा मैं घर बामा,
खेले लेते हो दिन चारी, दिन चारी
मैं घर बामा।
खेले लेते हो दिन चारी,
दिनचारी मैं घर बामा,
चारी
खेल लेते हो दिनचारी,
चारी मैहर मामा,
खेल लेते हो दिनचारी।
चारी मैहर मामा, खेले लेते हो दिन चारी, खेले लेते हो दिन चारी।
From coins to weapons. Tools to ornaments. Metals have played an important role in everyday life from the earliest known times till today. The association of mankind with metals began around 6000 BC when gold, the first metal, was discovered. Gold appears in nature in pure form, and that's why it was easiest for the primitive man to acquire. Stone Age man learned to fashion gold into ornaments.
Then another metal was discovered which also exists in nature in the pure form, and this metal was copper. The use of copper in antiquity is of more significance than gold, as the first tools, farming implements and weapons were made from copper. Copper was so important in shaping the civilization that the time period from 4000 to 2000 BC is commonly called the Copper Age. Then silver was discovered. It was used mainly for utensils and for ornaments. Iron was discovered around 3500 years back. Iron weapons revolutionized warfare, and iron implements did the same for farming. Iron was the building block for civilization, and the time period from around 750 BC to 50 AD is called the Iron Age. An iron pillar dating to 400 AD remains standing today in Delhi, India. Then gradually other metals were discovered. However, till 300 years back, only 12 metals were discovered. Then in the 18th century, 12 more were discovered. Rest of the metals were discovered during the last 200 years only. In fact, out of the total 114 elements that are known till date, 92 of them are metals, and the rest only 22 are non-metals. We know that metals have some special properties. All metals are lustrous, that is, they shine and glitter. Some metals can be beaten into thin sheets, even as thin as tissue paper. This property of metals is called malleability. Gold and silver are the most malleable materials. Metals are also ductile, that is, they can be drawn into thin wires. Gold is the most ductile material. In fact, due to these properties, metals can be shaped according to our desire into utensils, ornaments, and tools. Metals are hard, but there are some exceptions also. Some metals like potassium and sodium are soft. We can even cut them with knife. Here I will take out a piece of sodium coated with paraffin wax, and see, I can cut it with knife. When we cut a piece of sodium metal, the freshly cut piece appears lustrous. Other than being malleable, ductile and hard, metals are also a good conductor of heat. It is for this reason that we use metals for making vessels for cooking. They can absorb heat quickly and aid cooking. Of all the metals, silver is the best conductor of heat. Next best metal is copper. Aluminium is also a good conductor of heat. Obviously, we cannot have silver vessels to cook. Therefore, we have vessels made of copper, aluminium or iron. Another feature of metal that all of us know is that they conduct electric current. Of all the metals, silver and copper are very good conductors of electricity, followed by gold, aluminium and tungsten. But as silver is expensive, we use copper or aluminium wire for electrical works. While non-metals can be in solid, liquid or gas in their natural state, all metals are solid. Well, except mercury, which is in the liquid state. It is stated that mercury is the only metal in liquid state. However, as the melting point of cesium is only 21 degrees Celsius, in summers in India, even cesium could be in the liquid state. So is the case of gallium, whose melting point is about 30 degrees Celsius. And now the question arises, where do the metals come from? Metals are actually mined from earth. They usually occur in earth's crust. These rocky, sandy objects with metals are called minerals. Metals cannot be extracted profitably from all the minerals found in the earth's crust. Sometimes the amount or the percentage of metals in the compound is so low, or the rocks and the impurities are so high that extracting metals from it would be rather difficult or very expensive. Those minerals from which metals can be profitably extracted are called ores. Most of the metals do not occur in the pure form. They usually occur in the form of a compound, often contaminated with stone and mud. To obtain a metal in pure state from its ore, a process involving several steps is followed. After processing, the metals are obtained in pure form. We know that metals in their pure state have luster. Isn't that so? Then why is it that these metal pieces appear so dull? Let me now scrape off one of the piece and let's see what happens. The sandpaper. Well, now it shines. So why do metals lose their luster? It is due to the reaction that metals undergo when exposed to air. Most metals are very reactive with oxygen in the air and form metal oxide. As a result, they get covered with a thin oxide layer, and this thin oxide layer is the reason for the lusterless appearance. When we scrape this thin oxide layer, the oxide layer gets scraped off. Revealing the lustrous surface. However, gold is a class apart. Do you know that gold hardly reacts with oxygen? As it does not react with oxygen, no oxide is formed. Therefore, it does not lose its characteristic sheen. No wonder it is valued high. We have learned that metals react with various gases in air. Now let us observe how metals react with acids. we have added small amount of metal in each of these test tubes, but not before rubbing it with sandpaper to remove the oxide layer. This test tube has magnesium ribbon. This one has zinc granule. In this, we have added iron filings, and in this one there is copper turnings. Now, let us add approximately 5 ml of dilute hydrochloric acid in each of these test tubes and observe the reaction. You can see this is magnesium. See how fast the bubbles of hydrogen gas are emerging from it. The test tube also has become very hot. This is zinc, which is not far behind. This is iron. It is also reacting. But what about copper? There is no reaction at all. That means no reaction. When we repeat this experiment with dilute sulfuric acid, we obtain similar results. Do you remember grandma's advice not to keep tamarind, that is imli, in a metal vessel? Do you know why? Because tamarind has tartaric acid in it, and acids react with metals. Most metals react with dilute acids to produce a salt of the metal and hydrogen gas. In fact, most metals also react with water to produce a metal oxide or a metal hydroxide and hydrogen gas. Metals like sodium and potassium react even with cold water, and the reaction is so exothermic that the released hydrogen gas catches fire at once. Some metals like aluminium, zinc and iron do not react with cold water but react with steam. Metals like copper, silver and gold do not react with water at all. Now we know that reactivity of metals with oxygen, acids and water is different. But how do we find that which metal is more reactive than the other? Well, the more reactive metal can displace less reactive metal from its compounds in solution or molten form. Thus, by testing which metal is able to replace the other, we can find the relative reactivities of various metals. This is copper sulfate, a salt of copper, and this is zinc sulfate, a salt of zinc. Let us prepare their solutions in water. Zinc sulfate, water, copper sulfate and water. And now let us stir them to prepare a solution. Zinc sulfate solution. Wash the stirrer before you use it again. So, here we have the copper sulfate solution and the zinc sulfate solution. Now, we will put some copper turnings into the zinc sulfate solution and some zinc granules into the copper sulfate solution. And let's observe whether some reaction occurs. Observe carefully. The color of the copper sulfate solution has faded away, and you can see the deposition of copper at the bottom. This clearly shows that zinc is more reactive than copper, and so it has displaced copper from its solution, whereas copper has not been able to do that. By performing such experiments, the relative reactivities of metals can be found, and the metals have been arranged in the order of their decreasing reactivities. Potassium is most reactive and is followed by sodium, calcium, magnesium and aluminium. Zinc, iron, lead and hydrogen are the next lot. Copper, mercury, silver and gold are at the lowest rung. Actually, even before the relative reactivities of metals were found, people knew that gold, silver and copper are very less reactive. We may think that being strong and powerful is always better, but in case of metals, it is the opposite. A less reactive metal is always more precious. When we think of the word metal, what does come to our mind? An iron tool, a gold, silver or copper coin. But did you know that the salt that we eat, that this pinch of salt also consists of metal? It is sodium chloride, a salt of sodium. The vegetables that we eat are from the plants, the primary producers. But how do plants make their food? By photosynthesis. And how does photosynthesis occur? Due to chlorophyll. Do you know that each cell of chlorophyll consists of one single atom of magnesium? Without the metal magnesium, there would be no chlorophyll, and without chlorophyll, well, no photosynthesis. Do you know that iron forms an important part of our blood? Now, think of our body. The rigid structure of our body is due to the skeleton, and the skeleton is due to the bones. The bones get their strength from calcium. And what about calcium? It is another metal. In fact, metals give shape and strength not just to our body. Entire modern civilization is dependent upon metals. The Industrial Revolution is thanks to steel. Steel, which is a combination of iron and carbon with or without other metals like magnesium and so on. The jet age, space age is also due to use of metals like titanium. If the human past is pivoted with metals like copper and iron, it is the metals like uranium, titanium, chromium and magnesium which are paramount in today's economy. As for what metals will become the key part of our life in the days to come, no one knows. But perhaps you will find a new metal scattered on Mars or maybe a moon of Jupiter.
मानव इस सृष्टि की सबसे सुंदर रचना है और शायद इसीलिए मानव कुदरत की सुंदरता का सबसे कुशल चितेरा है। इंसानी हाथ और उसकी कल्पना प्रकृति के इस बिखरे सौंदर्य को रंग रेखाओं के माध्यम से कागज पर संवार देती है। कलाकार की प्रतिभा देखिए, कितनी सहजता से पेंसिल से कैनवस पर पहले प्रकृति के नजारे की बाहरी रूपरेखा उभारती है, फिर तूलिका के हल्के और गहरे स्पर्श से उसे सार्थक आकार देती है। कलाकार बड़ी सूझबूझ से जीवित भावों को चित्र में भरता है। देखिए, बैल की उठी हुई गर्दन, उछलते हुए अगले पैर उसके आनंद को दर्शा रहे हैं। पैरों के बीच की जमीन पर गहरे रंग गति के प्रभाव को उत्पन्न कर रहे हैं। पृष्ठभूमि का गहरा रंग, डूबते सूरज की लालिमा कठोर परिश्रम के बाद मिलने वाली राहत को अभिव्यक्त कर रहा है। आप भी खेत की मिट्टी से लेकर आसमान के बीच के संसार को अपनी तूलिका से ऐसे ही सजीव चित्रों में बदल सकते हैं। चित्र बनाने के लिए कागज का एक छोटा सा टुकड़ा ही काफी है। इन्हें देखिए, छोटी-छोटी सीप के खोलों में घुले रंग बड़ी से बड़ी कल्पना को बहुत बारीकी से कागज पर सजा संवार रहे हैं। यहां किसी बड़े तामझाम की जरूरत नहीं है। कला के प्रति निष्ठा हो तो साधनों की कमी बेमानी हो जाती है। और ये आग की लपटों को संजो रही कलाकार की तूलिका, मासूम नभचर और जलचर युद्ध की ज्वालाओं में झुलसकर जीवन की शून्यता को देख रहे हैं। हां, इंसानी घमंड की आग जो खाड़ी युद्ध में धधकी थी, जिसमें कुदरत के निरीह प्राणी मारे गए थे, उस आग से कलाकार का मन भी झुलस उठा था और उसकी कल्पना ने आग की लाल पीली लपटों को रंगों से उभारा। कलाकार ने अपनी आंतरिक पीड़ा को जैसे इन रंगों से उड़ेल कर रख दिया है। न जाने कितने आलंबन और उनसे उद्दीप्त अनेक भाव आते हैं, जाते हैं। कलाकार उन अनुभूतियों में डूबता है तो कृति अंकित हो जाती है। आपके परिवेश का ऐसा ही मुक्त चित्रण आप नए तरीके से बनाकर हमें भेज सकते हैं, जिसे देखकर आपके परिवेश का दर्शन हमारे दर्शकों को भी मिलेगा।
Human beings start to do experiments from the moment they are born. This baby is experimenting to see what happens to the small cup if he turns the big jar upside down. Whether anything more will come out, whether the small cup will go back in again, and what noise it'll make if he shakes it. These children, a little older, are experimenting with water. Now it goes into the jar. But if they turn the jar upside down, the water falls off the edges. And if they pour it through a soap dish, it makes a shower. A still older child experiments with the clay animal she has made. Can she get it to stand up? No? Try it again then. Each of these children is trying out ideas just to see what will happen, which is basically what a good scientist does. Unfortunately, many people have the idea that science can only be taught to older children, and even when it is taught, few teachers give their pupils the chance to do experiments. Science is seen as little more than the transmission of facts. For children in a class like this, it has nothing to do with the magic of asking questions and testing out ideas. How sad this is when the great age for experimentation is early childhood, when all of us are forever asking what and how and why. Children's natural aptitude for scientific investigation should be nurtured from the day they enter school, not allowed to rot until their spirit of inquiry has died under the weight of too much knowledge. In this program, we'll take a look at the kind of learning that goes on in one science lesson in a single teacher primary school. The children range in age between 3 and 11. It's a simple village school, and there's no money in the budget for science equipment. So the teacher makes do with a blackboard and a few things from her kitchen. Old jars, vegetable pieces, and some other odds and ends. She has only an intermediate pass, but has been trained in activity-based methods of teaching. The children are largely from disadvantaged homes, where there is no tradition of learning. Yet, with these few simple aids, the teacher is able to teach a lesson that involves all age groups in a genuinely scientific activity. Today, she asks the children to test a number of objects and find out whether they sink or float. She's not so much concerned to teach them facts. It's not very useful to know whether a rubber band usually sinks or floats. She is concerned with the development of a scientific way of thinking. It's the process of learning that matters, not the information taught. She starts off on a light note to give the children the feeling that science is fun, not a difficult chore. Then she takes her time to discuss the materials they're going to test, each time relating them to the children's own experience. This discussion sharpens their powers of observation, which are essential to scientific inquiry. Early on, she establishes that she's not looking for right answers. The children are free to express their own opinions. Throughout this discussion, she does not seek to teach facts, but to make the children familiar with the materials they will use in the experiment.
సరే నేను ఈ బొమ్మలు ఒక్కొక్కటి బోర్డు మీద రాస్తానా తర్వాత మీరు చెప్పాలి నాకు నేనేమడితా చెప్పాలా సరేనా నేను బోర్డు మీద ఏం బొమ్మ వేస్తాను
So as to include the non-readers, she draws each object on the board rather than write its name.
చూడు ఏం బొమ్మ ఇది సరే ఇప్పుడు ఏమైపోతున్నాను కాపిస్కా ఇప్పుడు జాజర్గడ్డ
This use of pictures as symbols enables everyone to participate in the lesson and is also a useful pre-reading exercise for the younger children.
చాక్పీస్ సరే ఇదేమంటారు చిక్కుడు ముక్క
Once the children are familiar with the items they're going to test, she asks them to guess which will float and which will sink.
ఇప్పుడు ముందరేముంది చొప్పబెండు ఈ సీసా నీళ్ళలో వేస్తే తేలుతుందా లేకపోతే మునుగుతుందా ఏమనుకుంటున్నారు మీరు తేలుతుంది అంటే చెయ్యి పైకి పెట్టండి మీ గుంపులో మీ గుంపులో మీ గుంపులో మీ గుంపులో ఇప్పుడు లెక్క పెడదామా ఎంతమంది చెయ్యి పైకి పెట్టారు 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21 22 23 24 25 26 27 28 29 30 31 32 33 అమ్మా ఎంతమంది ఇది సీసా కింది పోతుంది అనుకుంటారు
Again, she gives no indication that there is a right answer. They'll wait and see.
రెండు సార్లు చేయి పైకి పెట్టకూడదు నువ్వు కింది పోతుంది అనుకుంటావు నువ్వు నువ్వు ఓయ్ నువ్వు కింది పోతుంది అనుకుంటావు ఇద్దరు అట్టయితే సరే చూద్దాం ఇదేమిది టమాటా ఇది తేలుతుందా మునుగుతుందా తేలుతుందనే వాళ్ళు చేయి పైకి పెట్టు ఇక్కడ ముందర ఇక్కడ
As the children are being trained to think independently, they do not all follow the crowd.
ఒకటే తూరి చేయి పైకి పెట్టాలి మళ్ళా పెట్టకూడదు ఇక్కడ అక్కడ అక్కడ ఎవరు లేదు సరే ఇది ఎంతమంది తేలుతుందంటారు చేయి పైకి పెట్టు
The child at the back has the courage to stick to her own view, even though she is in a clear minority of 3 against 29. 500 years ago, it took a lot of courage to say that the world was round. A scientist sometimes needs to question majority opinion.
1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17
The numbers of children who guessed each way are recorded on the board. In this way, they learn to read a scientific table from a concrete experience, not the abstraction of a textbook.
1 2 3 4 5 6 7 8 9 10 11 12 ఎవరు కిందికి పోతుంది అనుకుంటారు
This first stage of prediction is essential to the process of an experiment. Most scientific discovery is made by people who say, I think this is what will happen. Let me test it out.
బాగా చెప్పినారు మీరందరూ చూద్దామా ఇప్పుడు ఏమవుతుందో మీరు చెప్పిన వాళ్ళంతా మీరే వేసి చూడండి ఒక కోటిగా ఇదిగో ఇది సీసా ఇవి అక్కడ బోర్డులో ఉండే వస్తువులు కదా ఇవి ఒక్కొక్క లైన్ లో పెట్టండి ఏమవుతుందో చూడు పెట్టు పెట్టు ఏమైంది చూడు చూడు ఏమైంది మీదనే ఉన్నది మీదనే ఉంది నువ్వేమనుకున్నావు మీదనే అనుకున్నావు ఏమైంది అది లోపలికి
The experiment is conducted by the children themselves. not the teacher. We learn how to do things, from cooking to riding a cycle, by doing them, not by watching other people. The children worked in mixed age groups so that the older ones can help the younger ones. But it is made clear that everyone has a turn in the experimentation. The children are eager to see which of their guesses were right. But there is no shame in their voices when they accept that they have been wrong. Being wrong is also a part of learning. Soon, each group has its results.
వచ్చింది పైకి కదా. ఏమి నువ్వు వేస్తుంది ఇప్పుడు రాజు?
However, the lesson does not end here. Afterwards, the teacher brings all the groups together to analyze their findings.
తర్వాత ఏమి? టమాటా. ఏమైంది టమాటా? అందరికి మునిగింది. నీకు మునిగింది. చూడు బాగా చూడు. చూడు 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 మీదికి వస్తుంది కదా. ఏమైంది అది మళ్ళా?
After a while, it becomes clear that not all groups got the same results. Most tomatoes sink, but one floated. Some shells floated if they were put in carefully, but some shells sank. From this, the children learned that there are variables in any experiment, and it is the discussion of the variables that often leads to real learning. It's not so important to learn the fact of whether something floated or sank, but it is important to search for possible reasons why the experiment turned out as it did. Did one rubber band float because it was lighter than the one that sank? Or was it flatter, smaller, made of a different material? Was it pushed down harder? As the children consider these possibilities, they use both their powers of observation and their problem-solving intelligence. What they are not using is their ability to memorize.
వీళ్ళది చూడు, ఇది పెద్దది పెద్దది అయినా తేలిందా ఇది? సరే పెట్టు.
These days, what we know about science changes from day to day. So memory should play a secondary role in the learning of science. What children need nowadays is an open mind capable of grappling with new ideas.
చాక్ పీసు దీని ఈ మైనం కంటే చిన్నది పెద్దది లేకపోతే చిన్నది. మళ్ళా ఎందుకు మునిగింది? తేలింది. అది అల్కగా ఉన్నది. ఇది అల్కగా ఉన్నది. అది అవునా?
The unexpected result should not be treated as wrong. It should be a leader to new discovery, because there's always a leader to be looked for.
ఎంతమంది టమాటకాయ తేలుతుందని చెప్పారు? 14 మంది చెప్పారు కదా. తేలిందా అది? మళ్ళా ఎంతమంది రైట్ చెప్పారు అయితే? 17.
After the results have been discussed, they are recorded. A ring is drawn around the number of children who guessed right. And here comes an interesting finding. Only 6 against 27 children predicted that the wax would float, but they turned out to be right.
ఏమనుకున్నారు? క్యాండిల్ తేలుతాననుకున్నారు. ఎక్కువ మంది ఏమనుకున్నారు చూడు. ఎక్కువ మంది ఏమనుకున్నారు? అనుకున్నారు. ఏమైంది అది? తేలింది కదా.
Here again they learn that the majority is not always right. Once children are taught to risk being wrong, they'll also have the courage to stick out for what they believe to be right. The implications of this go beyond science teaching. The capacity to think independently of the crowd is necessary to any responsible human being. Though simple, this lesson has helped to lay the groundwork for many important scientific attitudes. It has developed the capacity of the younger children to observe, guess, and classify. In addition, it has taught the older children to think about variables and to interpret the findings of an experiment. In all the children, it has strengthened an understanding of the scientific process of observation,
ఎంతమంది సీసా కింది పోతుందంటారు?
guesswork, experimentation, recording, and analysis.
ఇది అవునా? మళ్ళీ అది చిన్నదే పెద్దది కదా. అంతేనా? సరే.
Ultimately, this scientific process is far more important than the knowledge the children may have gained. Facts are usually forgotten within a month of the exam, but the capacity to think independently stays with us for life. All children know how to learn. They do it instinctively. And the method they use is play. These children are playing the local variety of hopscotch. Every time they get across the large rectangle without a mistake, they score 10 points. When they score 100, they get home to the small rectangle. No adult taught them this game. It has been passed from child to child. But from it, they're learning to count in tens and work within the order of group rules. Here is another game invented by children. As they sing, they make up the points of a square by intersecting their legs. In another similar game, they make a triangle. Self-taught lessons in geometry. When it is so clear that children teach themselves through play, why can't the teacher realize that play is a marvelous opportunity for effective teaching? Sadly, in most schools, play is just seen as an extra, a way of letting off energy after the serious business of work. Teachers often don't see that play can be the best work children can do. In this program, we'd like to take a look at the ways children can learn through play in the single-teacher primary school. Here, very young children are playing with sticks and leaves and shells. They are in fact classifying them into heaps. For them, it's a game. But the game has been organized by a sensible teacher who realizes that this kind of sorting activity is the beginning of learning how to think. While they classify the objects into sets, they also learn to count. Watch how one child corrects another as she miscounts the shells. In play, children often teach each other. Here is another group of very young children who are learning together. Their teacher has given them a bucket of water and a few odd cups. Simple materials. But what a lot they learn. They learn that water comes through a soap dish. But not through a cup. And then, if you turn the cup upside down, nothing goes in at all. Three small cups fill up the jar, and the children are beginning to understand what volume is all about. If a container has air in it, you can't push it down to the bottom. And if you push a cup down into water, it makes lovely bubbling noises. If a cup won't come off with your fingers, try your teeth. As the children play, they put their experiences into words, and so their thinking becomes clear to themselves. It's just as important for young children to talk as to listen. Playing with water gives them a new experience to talk about. This activity may seem relaxed and unprepared, but was in fact the result of thoughtful direction from a teacher. Teaching through play does not mean telling the children to go out and mess around. In fact, it takes more preparation and effort than the old rote learning methods. Before a class, the teacher should not so much ask, "What game shall we play today?" but "How can I turn what I teach into a game?" Here, a teacher has decided to teach the idea of seriation of size and the numbers 1 to 10 through the old team game Dog and the Bone. In this, she involves the older and younger children and uses the difference in their sizes as a teaching point.
అన్న వాళ్ళంతా ఒక అడుగు ముందుకేయాలి. రెండో నంబర్ వాళ్ళంతా మీరు ఇటువైపు నుంచండి, ఆ లైన్లో వీళ్ళు ఇక్కడ లైన్లో నుంచుంటారు. మీరు ఈ లైన్లో ఇట్లా పోతున్నారు, ఇట్లా ఎట్లా ఇందాక అట్లా నుంచున్నా అట్లా నుంచుకోవాలి.
Once the children are arranged from tallest to shortest, she makes 2 lines with rangoli powder. All teachers in South India will have some at home, so it costs next to nothing. Then she paces out the distance between the 2 lines and halves it to get the center point. Another useful mathematical activity. Through this, the children learn that a unit of measurement must be constant, like a foot's length. A stone is placed in a circle in the center. This is the dog's bone. The children are then numbered 1 to 10 in each team, according to their height. She makes sure that each child knows his own number. Then the game begins. As she calls out a number, the pair with that number from each team should run to the center and try to take the stone back to their baseline.
నంబర్ 2 2 1 అసలు లేదు.
If they do so without being touched, they score a point for their team.
నంబర్ 7
If they are touched, however, the point goes to the other team.
వీళ్ళకి 4 మీ 7 నంబర్ 1 నంబర్ 2 ముసలేదు ఇంకా రాయి గీత మీద నిలబడండి గీత
Though the children are almost unconscious of it, they have learned, in a practical situation, the concept of a constant unit of measurement, of seriation, and of the numbers 1 to 10.
1 2 3 4 5 6 7 8 9 బాస్ 11 12 13 14 15 బస్ 16 17 18 19 బాస్.
A good maths game for more advanced children is Buzz.
26 27 28 29 బాస్ 31 32.
The children count round the circle, each child adding a number. At multiples of 5, they should say Buzz and move out of the game. So do children who hesitate or make a mistake.
1 2 3 4 బస్ 6 7 8 9 బాస్ 11 12 13 14 15 బస్ 16 17 18 19 బాస్ 20 21 22 23 24 బస్ 26 27 28 29 బాస్ 31 32 33 34 బాస్ 36 37 38 బాస్.
The last child in is the winner. The game can be played with multiples of other numbers and is a beautiful, concrete example of the principle of multiplication.
బజ్ 51 52 53 54 55 సుధీర్ చెప్పాడు చేతులు దించండి.
Language, as well as maths, can be taught through a variety of games. Here is one which can be used to widen children's vocabulary of parts of the body, different verbs, feeling words, and much more.
నవ్వండి, పెద్దగా నవ్వండి. అవుట్. సుధీర్ చెప్పాడు నవ్వండి. సుధీర్ చెప్పాడు విచారంగా ఉండండి.
If she says, Sudhir Cheppadu, the children must do what she orders. If not, they must not obey her. If they do, they are out.
సుధీర్ చెప్పాడు ఆడండి. ఆగిపోండి. సుధీర్ చెప్పాడు ఆగిపోండి. అందరూ పుస్తకం చదవండి. పుస్తకం చదవండి. అవుట్. పుస్తకం చదవండి. సుధీర్ చెప్పాడు పుస్తకం చదవండి. పుస్తకం మూసి అక్కడ పెట్టండి. సుధీర్ చెప్పాడు పుస్తకం మూసి అక్కడ పెట్టండి. సుధీర్ చెప్పాడు మంచినీళ్ళు తాగండి. గ్లాస్ అక్కడ పెట్టండి. సుధీర్ చెప్పాడు గ్లాస్ అక్కడ పెట్టండి. నిద్రపోండి. అవుట్. సుధీర్ చెప్పాడు చేతులు పైకెత్తండి. చేతులు దించండి. చేతులు దించండి. సుధీర్ చెప్పాడు చేతులు దించండి. చేతులు ఇట్లా పెట్టుకోండి. పెట్టుకోండి చేతులు ఇట్లా. కోళ్ళం బట్టి. సుధీర్ చెప్పాడు చేతులు ఇట్లా పెట్టుకోండి. సుధీర్ చెప్పాడు ఇట్లా చేయండి. సుధీర్ చెప్పాడు చేతులు పైకెత్తండి. దించండి. సుధీర్ చెప్పాడు, చేతులు దించండి. అవుట్. సుధీర్ చెప్పాడు, పెద్దగా నవ్వండి. సుధీర్ చెప్పాడు, ఒక కాలు పట్టుకొని ఇట్లా గంటండి. ఇంకా నవ్వండి.
The last one in is the winner.
రా. Yeah.
The process of learning to read can be difficult for many children and needs to be livened up with as many reading games as possible. Bingo is one of the best. This teacher has prepared a set of bingo cards, each with a different combination of 30 simple, phonically regular words. She has sent the smallest children outside to play with water and gives those who are ready to read a card each.
Cha.
As she reads out the letters from her master list of 30, the children look for the letters on their own cards and cover them up if they are there.
Ka. E.
They help each other to find the letters. No game should be too competitive.
Ba.
The first one to cover all 6 letters shouts bingo.
Bingo. Da వచ్చిందా? వచ్చింది. సా వచ్చిందా? వచ్చింది. పా వచ్చిందా? వచ్చింది. బా వచ్చిందా? వచ్చింది. రా వచ్చిందా? వచ్చింది. కా వచ్చిందా? వచ్చింది. కరెక్ట్ గా పెట్టింది కదా తిను. ఫస్ట్ ఇమ్మాయి కూర్చో. జా. బింగో. కార్డ్ నా ఉంది కదా? ఉన్నది. పా ఉంది కదా? ఉన్నది. కా ఉంది కదా? ఉన్నది. మా ఉంది కదా? ఉన్నది. వా ఉంది కదా? ఉన్నది. తా ఏది? ఎందుకు పెట్టావు రాయి?
But oh dear, she's out. She covered a letter that hadn't been read out.
అవుట్.
So the game goes on.
గా. బింగో.
Games like bingo give early reading purpose and pleasure. Sets of cards can also be made for simple words to practice regular phonic patterns. Not all play is competitive. Children love to play at making things with their hands. Clay modeling develops the imagination and also gives young children control over their fingers in preparation for writing. Drawing and coloring, which to children are simply play, lead them to look at the world and interpret it in their own way. It's also a good pre-writing activity. Role play or drama is natural to all young children. When they play at being mothers and fathers, they learn about family relationships. When they pretend they are doctors or bus conductors, they put into words what they know about social relationships. This natural dramatic talent can be harnessed by the teacher in social studies lessons. Here, the children are acting out being in a shop.
ఎంతున్నాయబ్బా 6 రూపాయల కోటి 5 లేదు 6 రూపాయల కోటి నీ మనసు తీసుకోలే లేదు.
The goods for the shop have come from the teacher's kitchen for the day, and the children learn to handle real money.
ఇంట్లున్నది 5 ఏడా 5 రూపాయలు 5 అవి కాదు 4 రూపాయలు 4 రూపాయలు 5 ఉన్నాయి ఇవేమై రూపాయలు ఐదు 5 రూపాయల నోట అదే 8 రూపాయల కోటి
4 రూపాయలు ఉన్నాయి.
They learn to bargain.
8 రూపాయల కోటివి అవి 10 రూపాయల కోటి అవి 6 రూపాయల కోటి
4 రూపాయలు ఉన్నది.
4 ఏడున్నది
ఇదేమది 4
కాదు 4 7 రూపాయల కోటి
4 ఉన్నది. స్టీల్ లేకుంటలేదు. మస్తు దుకాన్లు ఉన్నాయి.
మస్తు దుకాన్లు ఉంటే తెచ్చుకో.
4 రూపాయలకి
లేదు లేదు 7 రూపాయలు ఉన్నది 1 రూపాయి దించేస్తున్నా.
ఏమే 4 రూపాయలు ఉన్నది ఎక్కడ 1 రూపాయి దించేస్తున్నా.
4 ఉన్నదమ్మా 7 రూపాయలు ఉన్నది.
4 రూపాయలు ఉన్నది మళ్ళీ ఎక్కువ చేసుకుంటే దించేస్తున్నా.
ఎన్ని ఇవి
4
రూపాయి 2 రూపాయలు 3 రూపాయలు
ఇది 2 ఇవి 2
రూపాయి లోటు
ఆడా
ఇదేమది
నీకు బాగా తెలిసేటట్లున్నది. 2 రూపాయలు ఉన్నది చూడు.
2 ఇది
3
ఇది
4
రూపాయలు అవుతాయి.
మరి
And they learn to cope with the shopkeeper who keeps them on their toes by cheating whenever she can.
రూపాయి ఐదు కాదు ఆటానా
రూపాయి
కాదమ్మా చూడు నీ మనసు అది ఆటానున్నది ఇది
ఇక ఈడ రూపాయి లేదా ఇగో
రూపాయి ఐదు పటాయి.
This type of role play does more to prepare children for the real world than any textbook can.
4 రూపాయలు లేదు ఇగో తీసుకుంటావా లేదా మరి తీసుకో.
In the last few minutes, we've looked at games for pre-literate children: sorting, water play, clay work, and drawing. We've seen an early maths game and a more advanced one. We've looked at language games, both for listening and for reading. We've seen a role play game in a social studies lesson.
రూపాయి 2 రూపాయలు 3 రూపాయలు
ఇది 2 ఇవి 2
4
And to go back to where we started, the games children invent for themselves. For almost any lesson you teach, ask yourself, how can I turn this lesson into a game? All it takes is a little imagination. Even though a teacher has to work harder to think of the right game for the right situation and to control the excitement she whips up, her effort is always worth the trouble.
मित्रों, आपको हमारे कार्यक्रम कैसे लगे? आप अपनी प्रतिक्रियाएं और सुझाव हमें भेज सकते हैं. हमारा पता है किशोर मंच, CIET NCERT, श्री अरविंदो मार्ग, नई दिल्ली 110016. आप हमें ईमेल भी कर सकते हैं. हमारा ईमेल पता है ciet.kishoremanch@gmail.com और हमारे टोल फ्री नंबर हैं 1800111265 और 1800112199.